Hey guys, and welcome to the full course on battery management systems, your comprehensive guide to understanding the backbone of modern electric vehicles and energy storage systems. This is a certified session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we are dedicated to offering advanced industry-relevant engineering courses crafted by industry experts. Don't forget to subscribe to our channel for more insightful tutorials and updates on engineering tools and technologies. Hit the subscribe button below and stay tuned. Here is a brief overview of what we will cover in this training video. In the first chapter, we will introduce you to the types and classifications of BMS based on functionality and voltage levels. You will understand the differences between low voltage systems used in typically two-wheelers and three-wheelers and the high voltage systems for applications like buses, cars, and off-road vehicles. In the second chapter, we will explore the architectures of BMS. This includes centralized systems where a single board performs all monitoring and control functions, and decentralized systems featuring battery monitoring units and battery control units in a master-slave setup. In the third chapter, we will discuss the need for decentralized architecture in high voltage applications. You will learn about challenges like long wiring harnesses, noise interference, and some common reliability issues, as well as how decentralized systems provide scalability and improve performance. In the fourth chapter, we will provide an overview of wiring harness systems in BMS. This includes voltage sensors, temperature sensors, and power distribution units. You will also learn about safety critical elements like fuses, contactors, and precharge circuits that protect battery packs. In the fifth chapter, we will dive into cooling plates and their importance in thermal management. You will learn about material choices, integration techniques, and the design factors necessary to ensure efficient heat dissipation and structural reliability. In the sixth chapter, we will examine abusive usage conditions and how BMS safety protocols are designed to prevent capacity degradation and ensure long-term battery performance. Topics include overcharging, high operating temperatures, and how BMS limits are programmed. In the seventh chapter, we will review real-world case studies on low-voltage and high-voltage BMS systems. You will analyze design configurations and functionalities for two-wheelers, three-wheelers, and high-capacity electric vehicles like buses and trucks. Thank you for joining us. We are thrilled to have you on this learning journey. Make sure to subscribe to our channel for more updates and detailed tutorials. Complete this session, earn your certificate, and share your achievement with your network. Let's get started with battery management systems and unlock the potential of cutting-edge energy management technologies. Thank you.
Everyone, I would like you to welcome to the course on lithium-ion battery practice and considerations. And as you know by now, where EV has become a current trend and it's going to be the future of the mobility, where lithium-ion battery pack is the most important power source of the whole electric vehicle, which makes the whole focus on lithium-ion battery pack to be safe. It has to be robust enough to handle a lot of shocks, vibrations, etc. So this course will be mostly focusing on those considerations needed for a very good battery pack design. So since this is a very huge topic, we'll have this whole course split it into 3 different weeks, and sessions of this week would mostly focused on lithium-ion battery pack design considerations, cell basics, cell sizing, selection of cells, what are the different form factors available, what are the different chemistries that lithium-ion has, etc. And also we'll also have certain sessions where we'll also focus on what is the right cell selection for making a pack, because each application has its own needs and we'll have to choose the right cell, which is the most important part. So we'll get into the table of contents. So this session would mostly focus on lithium-ion cell chemistries, what are the form factors of the cell, what are the different cell configurations like series combination or a parallel combination or a combination of both, which are needed to make a module. And then we'll also focus on what are the factors needed for selection of a cell. And then we'll have a case study followed by that to understand what do we need to do to select the right cell. Then we also get into understanding of how to design pack, which is from cell to module to pack. We'll also understand what's the process involved in that. And then we'll also have a subtopic where we'll have to understand what are the considerations for design of a module. So since we have different form factors, we'll understand each form factors design considerations for the module. And then since we concentrate on the case study, that leads to more elaborated understanding of prismatic cell module design also. And also we'll understand what are the different components in the battery pack, and what are its roles in the battery pack, what is important, how does it play a vital role, etc. And what are the robust pack requisites, because battery pack being the whole power source, it has to be handled safely. So what are the most important aspects that it has to sustain, it has to withstand loads, shocks, vibrations, thermal loads, temperatures, etc. And then we'll also understand what are the wiring harness designs, what are the power cables used, because power cables being the primary source for transferring the electric current from the cells to the motor. We'll also have to choose the right cell and also a right power cable. So we'll also understand what does that mean. Now when we go to the learning objectives, as we saw in the previous slide, this would be the objectives of the session for this week, which is mostly where we'll understand on what are the operating voltages of lithium-ion cells, what are the different form factors, different sizes, different shapes of lithium-ion cells, and also what is the right cell selection for the application, which is basically based on the C rates. We have an EV which is working at 1C or 0.5C, etc. So this is something which we hear quite often. So we'll understand what are the C rates, and then we'll also understand what are the capacity of the cells, packs, modules, what are the cell sizes available in terms of dimension, in terms of capacity, etc. What are the vehicle volume, which is like if there is a space, in that space we need to fit a battery pack. Is the space sufficient or not? If it's not sufficient, how do we make our battery pack such that it goes and sits in that place? So vehicle volume plays a very important role. So we also need to see that when we select a cell, it is compact enough to fit into the vehicle volume. And then we'll also understand what are the motor nominal and peak ratings, and according to that, how do we size our battery pack. And then we all focus on what are the series parallel combinations of modules, because module consists of cells and battery pack consists of modules. So we'll have to make a right combination of cells in series and parallel to get the right battery pack specification in terms of voltage and capacity. And what is the process of conversion from cell to module to pack. And this lithium-ion battery pack, when we say it is a combination of lot of components which are electrical, mechanical, electronics, etc. And each component has its own purpose, has its own role. So we'll also understand what is its role, what are the different components involved, which would give a fair idea of what is its need and how does it help in the whole battery pack design. So we'll move to the course introduction. So as you know, this course mainly focuses on design procedure carried out from selection of a cell to making a battery pack. So the different process steps involved in designing a module, which involves like thermal designs, and mainly thermal is one of the most important parts. So when we have a cell, there is not just one cell available. There are different types of cells available, and selecting the right cell for an application is something the most important task for a battery engineer. So this course would help you, in realizing what parameters are to be looked at in a cell data sheet and choose the right one. So we'll also have a good emphasis on electronics, wiring harness, which would include different types of sensors, BMS architectures, high voltage, low voltage, how BMS architecture looks like, what is its functionalities, so what is the performance of battery pack, what are different assembly processes involved in cell to module making, and then to pack. So not just that, we'll not limit over there. We'll also understand what are the different kinds of ingress protections needed to make sure that the pack is sturdy. And ingress protection is something like a foreign object like water or dust enters into it. So that is also a most important part for a battery pack design. We'll also understand those aspects of the battery pack, and we'll also understand the thermal aspects of the battery pack. Like if there's a cell, if it is discharged or charged, there is a certain amount of heat being generated, and it's very important that has to be removed. So we'll also understand what are the thermal loop designs for a battery pack. So this course would concentrate on everything that is needed for a battery pack, right from cell selection till the whole assembly process. So let us get into the course now. So before that, let us have a small idea on what are the prerequisites for the course. So this course would be interesting, and if you already have some understanding on different lithium-ion chemistries electrical wiring, electronics, that knowledge would definitely help you in giving more interesting aspects on this course, how it's going to be. Or else nothing to worry about, because this course, as we go on through the slides, each and every basic are already been touch base, so you'll understand it very easily, so shouldn't be a problem. But what are the main skills required? Is like there has to be a certain level of understanding on what are the different lithium-ion chemistries, a little bit of knowledge on electronics, electrical, basic knowledge on the relations between current, which is basically Ohm's law, current, power, resistance, voltage, etc. A little bit of knowledge on thermal studies, like thermal conduction laws, convection, radiation laws. How do you calculate the heat generated, etc. So this is basically a cross multi-domain functionality course. So nevertheless, we are going to touch base on every topic, and wherever there is a need of any basic behind it, we'll definitely cover in that. That is being covered in this course of sessions, which will help you in understanding what is it, how is it happening, and why is it happening. So there's nothing to worry about that. So now we'll go to the course, which is the first topic, which is lithium-ion form factors and chemistries. So when we say lithium-ion form factors and chemistries, form factor is nothing but how does a cell look like in terms of sizes, shapes of the cells, etc. Usually when we say lithium-ion battery pack is the bigger one. So battery pack consists of cells. So that is this cell. So when we say lithium-ion cell, it is referring to just a cell, which is this cell. Or it's a cylindrical cell, or it's a pouch cell, or a prismatic cell. So mostly lithium-ion cells are in 3 different form factors throughout currently available, which is cylindrical cell, which is pouch cell, and prismatics. So apart from these 3 cells, there are also coin cells, which you might have seen in your wristwatches, tiny small cells which are circular in shape. But small cells means, smaller capacity. Hence, when we have to use it in EV, an EV needs a lot of capacity, a battery pack. And when such cells are used, you need to combine a lot of cells to be added in parallel, which will give a huge resistance of welding when they are welded together. So it makes it quite difficult for the manufacturers when such tiny cells are used. Nevertheless, but these small cells are used in the R&D labs by the electrochemists to conduct small experiments, because making such a big cell would be time consuming, would be a lot of energy has to be put in, a lot of money has to be put in, which for the R&D purpose, which is not feasible. So small cells are used for this one. So basically we have these 3 cells, cylindrical, pouch and prismatic cells, which is majorly used for EVs. And then when we say cylindrical, pouch and prismatic, each cell has its own advantages and disadvantages. For example, Tesla uses cylindrical cell, BYD uses prismatic cells. So why do they use in each cell? Because it is their flexibility of design, it's their easiness with that technology which is being used. So when we say a cylindrical cell, basically cylindrical cell has been commonized throughout the world right now, and it has been commonized so much that throughout the world there is only some formats being used, like 18650, we have 2170, 3270. So when we say 18650, that is related to a cylindrical cell, and when we say 18650, 18650, the first 2 digits, which is 18, resembles to the diameter of this. And when we say 65, 18650, which is the length or height of the cell. So that is the cylindrical cell dimensions when we represent it as 18650. Similarly, when we have 2170, the first 2 digits resemble the diameter, and the next 2 digits, which is 70, resembles the height. Similarly, we have pouch and prismatic cell, and these are not yet commonized because these are cells with much more higher capacities. So that's the reason this has not yet been commonized. But when we talk about the form factor, we have cylindrical cell, which all has a shell of a cylindrical shape, and which is mostly an SS or a nickel. And when we have pouch cells, which is the second one, if you see, this is quite thin, and the cover or the enclosure used is an aluminium foil. This cell, pouch cell, is able to hold a lot of capacity compared to a cylindrical cell. A cylindrical cell can have typically up to 5 Ah capacity, whereas a pouch cell can hold up to 60 to 70 Ah of capacity, which is way high than what a cylindrical cell can hold. Same is the case with the prismatic cell. A prismatic cell can hold a capacity of 200 Ah. And if you see how much of the capacity is held in prismatic cell, It is way higher than the cylindrical cell. But the common difference you might have noticed over here is prismatic cell has a shell which is like 0.8 mm thick. Aluminum can is being used for a prismatic cell. Whereas for a pouch cell, a thin aluminum sheet is being used for this. That makes the name, which is pouch cell. It's a pouch-like structure, or the membrane is being used to enclose the whole pouch cell. Whereas the prismatic cell uses a can, which helps in its own structural rigidity, whereas pouch cell has a little bit of a disadvantage there. So this is how the form factors of a lithium-ion cell is. Cylindrical, pouch and prismatic each has its own advantages. Cylindrical cell being small, it can be flexible, you can put it in any direction, any orientation, any shape. Pouch and prismatic cell are mostly common, you can arrange it in only rectangular ways because of its shape and the nature of its cell. Now let us understand what are the lithium-ion chemistries. So one common myth is like lithium-ion, not many people understand, like when you say lithium-ion, it's a common chemistry, it's a single chemistry, but no, like lead acid or nickel zinc, no, lithium-ion is not like that. Lithium-ion itself consists of a lot of chemistries, like we have lithium iron phosphate, LFP, and then we have nickel manganese cobalt, NMC or NCM, and then we have lithium titanate oxide, LTO, and then we have lithium polymer, LiPo. So just to touch base on how a lithium-ion cell is constructed, we know lithium-ion, any cell will consist of a positive and a negative anode and cathode. So this chemistry which we talk about, LFP, NMC, LTO or LiPo, are the cathode components of a cell, which is the positive. And the anode is going to be mainly graphite or a carbon, which is the anode, which is the negative element. And both cathode and anode are separated by a separator, which is a thin membrane, which is a nano-sized membrane which allows the ions to flow across. And that's how the ions pass through the membrane, which is called a separator between anode and cathode, and that's how the charging and discharging process occurs. So when we say that the cell has been short-circuited internally, which means the separator which is being used has been punctured because of these ions passing. So that is the reason we say the cell hasn't had an internal short circuit and the cell has failed. So basically a cell is a combination of a cathode, anode and a separator, etc. And each material used for a cathode like LFP, NMC or LTO will have its own electropotential voltages. So that's how the whole chemistry changes the whole voltage window of a lithium-ion cell. For example, each chemistry over here has a different voltage window, and this combination of materials in a cathode also determine the energy density, also determine the C rates, also determine the life cycles of the cell, etc. So these are the initial cathode components which are playing a vital role in selection of a cell as per the application. For example, LFP, lithium iron phosphate, has a higher life cycles when compared to NMC, but it cannot give higher C rates when it compares to NMC. Similarly, lithium titanate oxide, it has higher life cycles, it has higher C rates, but it is way heavier than what an LFP or NMC is. So it's all based on chemistry materials, based on cathode materials and their respective phenomena, which are unique for their own, and it has to be based on the selection it has to be chosen. Now we'll understand what are the different form factors and its advantages and disadvantages. As we now understand that there are three different form factors, which is cylindrical, pouch and prismatic. And we also saw how are the construction done. Cylindrical cell is basically done in a can. Pouch cell is using a pouch foil as an aluminum enclosure, and prismatic cell is basically in a steel can. So because the constructions, the process of manufacturing involved are completely different, each cell has its own advantages and disadvantages. So mind you, I would like to remind you that cylindrical cell is a cell which is having the lowest capacity. The maximum cell capacity possible is 5 Ah currently. And then we have a pouch cell which has a decent capacity it can hold, like 60 Ah or 65 Ah. And then we have prismatic cell which tops the whole list, which can hold up to 200 Ah also. Now when we talk about advantages and disadvantages of these form factors, which are the primary motives for selection of a cell with respect to form factor, when we have a cylindrical cell, Cylindrical cells are basically available in all small sizes, as we see, like 18650 and 2170, which means 18 mm dia and 65 mm height, which is a quite small number. Being at a small size, it helps in flexibility of arrangements in series and parallel combination. So this is something where you can orient it in any direction so that you can get the required capacity. It's just that you will need more number of cells in series and parallel combination, but when you have space, when you have the flexibility, you can do it in either ways. So that is one thing which the cylindrical cell users take advantage of, primarily being Tesla. It's the only car manufacturer who uses cylindrical cells, and that's the advantage which they see in it. And also another advantage of this is cylindrical cells have a cylindrical can, which is of TICL or SS, anything. And if you go into a little bit of basics of mechanical engineering, you could identify that a cylindrical object or a cylindrical shell will have a higher hoop stress against internal stresses. Since the cell is tend to charge and discharge, there would be always an expansion and contraction in the electrodes, which will allow the cell to expand and contract, which means after a certain point of time, when after 10 charge cycles or 100 charge cycles or 200 charge cycles, when you suddenly see, you might observe the cell is little bit bulged, and that you cannot see in a cylindrical cell because of its nature of construction having a cylindrical can around it. So that is one of the reason why cylindrical cell has an advantage, where other cells like pouch cell, prismatic cell will require a lot of pressure plates, thermal foams, etc. to hold that kind of expansion, whereas cylindrical cell will not need it. And when we go to the disadvantages, if you see the cylindrical shape, because ultimately when you make a battery pack, it has to be in a square or some kind of form. Since the cylindrical cell is round or circular in nature, if you take a square and you fit the cylindrical, all the four corners are the loss of areas. So those areas, when you put a lot of cells together, you will have a loss of required area. So that area is not being filled up. So unless you use a phase change material or a thermal dissipation material and fill it there, it's of no use currently. So that is how you lose area while using a cylindrical cell. And also you also have a challenge in extracting heat from the cells. So because there is no flat surface anywhere in the cylindrical cell, the way you extract heat from the cylindrical cells becomes quite difficult. And then you have pouch cells. So pouch cells, as we discussed, like pouch cells are available in very big capacities like 50 Ah or 60 Ah, so which is not the case for cylindrical cells. Now, for example, we need a 50 Ah capacity with a single pouch cell. Whereas if we want to do that with a cylindrical cell, we'll need to have 10 cells of 5 Ah put in parallel together. So when we do that, when we are paralleling the cells, the bus bars used for connecting one cell to another cell in parallel, which means we'll have 10 interconnections. Each weld joint will have its own internal contact resistance. I would say contact resistance that would add up to the heat. Instead, if you use one pouch cell, it makes the whole job easy. So that is how you have a great advantage with pouch cells. And then another big advantage is heat dissipation. Unlike the cylindrical nature of the cell, you have a pouch cell which has a flat area, and when you have a flat area, you can put any of a conducting material or a heat sink over there, and you can extract as much as heat possible from that. So that is one of the great advantages that you have with a pouch cell, because it has a large area, and since the capacity is high, it tends to generate heat, and that heat could be easily removed from the cell. So that is one advantage, and because of its high weight, and also a very thin enclosure material is used around it for as an enclosure sheet, which makes the cell a little bit lighter when compared to SS can or aluminum can for a prismatic cell. Hence you get higher energy density, which is watt per kg. Now this is how you get some benefits in pouch cell, but it's not just that. Now each cell will have its own disadvantages also when compared to advantages. That is, when you put some 10 or 20 pouch cells together, this pouch cell has a very thin enclosure material, which is a foil, and it tends to expand over a period of time. When that expands, you will need a lot of pressure plates to put across to hold that expansion, which could be thermal foams, which could be cell holders, which could be heat carrier plates. You put everything across a cell, and then you tighten it very hardly against the torque. Like this values of torque for tightening and applying pressure on the cells is completely achieved through a thermal simulation. By understanding the cell testing or physical testing has to be done on the cell, and those values are used for the structural simulation to understand the expansion, and those values are taken to put the reverse pressure on the cells so that you can hold the cells against expansion. So when you see that, there's a big process involved, and it would definitely expand over a period of time. And also, to hold that kind of expansion, you will need a lot of components required, and that makes the whole process complex. And then we have a prismatic cell. So prismatic cell is even more capable of holding much more higher capacities. And since this is a shell, it has an aluminum can, and the whole electrodes, cathodes, anodes, separators are put in that. The module design becomes easy because each cell itself holds a higher capacity. And unlike the pouch cell, now if you see, we have a pouch cell and we have a prismatic cell. This prismatic cell is thicker than a pouch cell. So, which means this doesn't expand like how a pouch cell expands. So you don't need a lot of pressure plates and a lot of holding materials for a prismatic cell as compared to a pouch cell. So that makes the whole design a little bit easy. And then one disadvantage is sizes. Prismatic cell is very big in size, and when you want to use prismatic cells with such high capacities, you definitely cannot use it in a two-wheeler. So that is one of a problem. Either you'll have to design a customized two-wheeler prismatic cell for a small size so that you can fit it in a two-wheeler, or else high capacity prismatic cells can never go in a two-wheeler bike. And then another disadvantage, or it could be a challenge, is usually prismatic cells can be welded. I mean, one cell to another cell. When we want to connect one cell to another cell, there are different ways to do it for a prismatic cell, which could be a laser welding, or you could tighten them with a nut and bolt. So when you use such kind of nut and bolt system, the contact resistance between the bus bar and the cell is a little bit challenging. It is high when compared to a very good weld joint. So that is a challenge that you would face in the prismatic cell. Now we talked about flexibility of the cylindrical cells. Here we would see how the flexibility of the cylindrical cells can get affected and what are the advantages in those arrangements of the cylindrical cell. Now first one is a straight arrangement. We could see all the cells are arranged one beside the other. Now when I said there's an area loss, I am talking about this area. So this area is nowhere to be filled. Now how effective we put the cells, we reduce the gap between each other, and even the package it. This is some area which you would definitely lose in common. So to avoid that, you could do a zigzag arrangement where some of its area has been utilized, but still you have certain voids formed between the two rows or three rows, etc. So that is how you will find that there is some loss in area when it comes to cylindrical cells, whereas when it's in pouch and prismatic cell, because of the rectangular nature, you won't have such voids of spaces forming. Now we would enter into lithium-ion voltage chemistries for different voltages and its chemistries, etc. So the whole lithium-ion voltage window is divided into three different types. We have a nominal voltage, which is also called as open circuit voltage, which is like when a positive and a negative electrode are put together, there is a certain potential which happens to be there, which tends to give a nominal voltage, also called as open circuit voltage, nominal. And then we have a maximum voltage, and then we have a minimum voltage. So maximum voltage is the voltage when you fully charge the cell, and that is how you reach a maximum voltage window. And minimum voltage is when you fully discharge the cell, you reach a lowest point of the voltage window, that is called as the minimum voltage. And when we have different chemistries like lithium iron phosphate, nickel manganese cobalt, lithium titaniate, lithium polymer, each cell has its own voltage window. Now here we see LFP, which has a nominal voltage of 3.2 volts, and then we have a maximum voltage of 3.6 volts and a minimum voltage of 2.5 volts. Which means when you have a cell and it is charged to a maximum voltage of 3.6, it can be discharged to 2.5 voltage. We have NMC, which has a nominal voltage of 3.65 or 3.7 volts, and when it is charged, it can reach up to 4.2 volts, and when it is discharged, it can reach up to 3 volts. So which means the working window of these cells are basically from 2.5 to 3.6 volts for an LFP, 3 volts to 4.2 volts for NMC, 1.5 volts to 2.8 volts for LTO with a nominal voltage of 2.3, and lithium polymer is somewhat closer to what a nickel manganese NMC cobalt cell is, which is similar almost 3.7 volts. When charged, it goes up to 4.2. And when discharged, it comes up to 3 volts. So this is the voltage window for the lithium-ion polymer cell. So these are all chemistry voltages are all dependent on the cathode materials which are being used, and these are certain values which are quoted as per the generalized values. Usually it depends also on the OEM till what extent they can provide. For example, in some OEMs or cell manufacturers can give a nominal voltage of 3.55, and they say that they can go up to 2.8 volts, which is when discharged, it can go up to 2.8 volts. So it depends, it changes from cell chemistry to cell chemistry or the material composition being used, whereas NMC is going to be the common, but there could be some additives or some dopants which are going to be used, which makes this kind of changes. So that is some secret ingredient which they add to have some advantages, like it can allow higher C rate operations, or it can allow operating at higher temperatures, or it could lead to increase in the life cycles. So there could be multiple factors why this open circuit voltages or the maximum and minimum voltages can differ, but it is done with a certain intention to get some advantages out of it. Now we'll understand what are the different cell configurations, which is how the cells are arranged in series and parallel combination to make a module. Remember, a module is a combination of cells which are arranged in series and parallel. So let us go through that. Now here we have a table where we can see different combinations: 12S1P, 1S12P, 6S2P, 2P6S, 4S3P, 3S4. Now we have a cell configuration slide where we have 12 cells in a module with 3.7 volts and 50 H capacity of a cell. So if you see 12 cells, we have different combinations or series and parallel configurations formed, which is like 12S1P, 1S12P, 6S2P, 2P6S, whatnot. So what does this mean? This means, as if we refer to the basic formula of Ohm's law, which is V is equal to IR, which says if we connect n number of cells in series, the voltage adds up. If we connect the same n number of cells in parallel, your capacity builds up. So we are following the same formula over here. It's just that a module has 12 cells and we are going to connect 12 cells in series, which will lead to 44.4 volts for a module. And we have each cell capacity being 50 H, and since there is no parallelization, we have 50 H for that, which means the module of 12S1P configuration will have 44.4 volts and it will have 50 H capacity. Now similarly, if we have a module with 1S12P configuration, we will have a module with only 3.7 volts, but the module capacity will be 600 H because 12 cells are connected in parallel. Similarly, if we see 6S2P, which means we have 6 cells connected in series and 2 cells connected in parallel, which will give 22.2 watt module level voltage, and will give 50 Ah times 2, which is 100 Ah of module capacity. So that's how you can try different combinations in a same cells module. Unless you have two modules or different voltages, you cannot connect that, because high voltage and low voltage can always have a potential difference, and the voltage would always flying from high voltage to low voltage. So when we have to connect multiple modules in series, it's to be important that all the modules have to be of same voltage and they are to be connected in series. It's easy in that way. So that is how we have different combinations arranged at a module level. When we have n number of cells, they have to be carefully selected in series and parallel combinations, so that you connect all those modules together to get the right pack voltage and capacity. Since we have understood till now what are the different form factors, what are the different lithium-ion chemistries involved, what are the advantages and disadvantages of the form factors, and how the module configurations are done, now we'll understand what is the driving factor for the cell selection, what are the important needs for selecting the right cell. So here we have listed down a few factors for a right cell, which is like, if you want to select a right cell, we need to have the following factors, like motor rating, what is the continuous and peak current requirement, and what is the operating voltage window of the motor. Motor ratings are something which drive the battery pack specifications, like in terms of pack voltage, which means the battery voltage should be maintained within that motor voltage window throughout the drive cycle. Or else you can see sometimes the motors or the fans at your home run at a very slow speeds. It's because of low voltage. The same would happen over there also. It's a daily life application example which you'll find. So the motor rating and the motor voltage window should be at least equal to that of a battery pack voltage window. So that has to be considered first. And then we have target range, vehicle's target range, which is how many kilometers that the vehicle has to achieve in one charge cycle, which is basically deciding on the capacity of the battery pack. If you have a higher capacity, the more kilometers you can get. It is like the petrol tank in ICE engine vehicle. The bigger petrol tank you have, you can travel longer kilometers. It is the same. So that is how you decide on the capacity of the battery pack. And then once all these like battery pack voltages, battery pack capacities are decided, then the most important part that you need to understand is the vehicle C rate requirement. What is the vehicle C rate requirement needed over here, which is for accelerating the vehicle, which is when you want to overtake, when you want to go at a certain speed or higher speeds, what are the C rates required. And this doesn't only require, when you say accelerating, which is called the discharging current, and when you say accelerating and moving faster, it becomes peak current. So there are different kinds of C rates like continuous current, peak current, and this is for both charging and discharging. So when you say continuous current is something when the current is quite stabilized, when you're going on a flat road and you're going at a normal speed of say 45 kilometers per hour or 50 kilometers per hour, where you're not interested in overtaking some other vehicles, you're going at a pace. So that is how, which is called as a continuous current. So you don't draw a lot of current over there, which is called as a continuous discharge current. But whereas when you want to go somewhere quickly and you want to accelerate many a times, which is dependent on the motor's capability and also the battery pack's capability, and that has to be matched often. So that means if the motor is capable of taking more power, it's capable of delivering more thrust to the vehicle, but the battery pack is not designed for it, you need to really look into that. You stop saying that this battery pack is capable of giving only this much, I have only this amount of power that can I offer, and don't ask me for more. So you will program this in the BMS saying that this is my limit and I could give only to this, and the motor will deliver only that. So that means your motor would be highly sized and your battery pack is not going to deliver such C rates. Then the whole performance of the vehicle goes down. So you'll have to understand what is the C rate of the motor, what is the capability of that the motor will deliver, and there is a real need that or not, and then you choose the right cell for that application. So that is how your peak C rate comes, peak discharge rate. So whenever you're moving on the vehicle, everything that you are doing on the vehicle in motion is going to call, and when your vehicle is stable and you put on a charger, that is called a charge current. And C rate is something which is associated with that. How fast you want to discharge, how fast you want to charge the vehicle is nothing but C rate. So this is how the whole C rates have been arrived at. Like it's called a continuous C rate, it's called as a peak C rate. So basically charges currently in India are continuous C rate. So you fix the charger to the vehicle, it will be charged at a continuous rate. It's a standard rate. So whereas when you say discharge, it's always dynamic. You cannot expect a single C rate or a single rate at which the discharge would happen, because it's a road. You will accelerate, you will decelerate, you will brake the vehicle, etc. So that is how your C rates are important. So that plays a vital role in selection of the right cell. So another important feature that you will have to take care is the life cycles and the operating temperature of the cells. So one charge and discharge cycle is termed as one cycle. So which means when you say one life cycle, it has completed one charge and one discharge together. So this life cycles of the cells, they are decided on how many number of charge and discharge cycles you can deliver when you reach to a capacity degradation stage. In simple terms, like the working life of a cell has been exhausted. So typically for EV applications, when they degrade to 80% of their capacity deterioration, you put out the cells from EV, you don't use it for electric vehicles anymore. You could use those for storage or any other applications, because after 80% of degradation of this capacity, they won't be able to deliver such high C rates like 1C, 2C and 3C. So here I would like to give a little bit of emphasis on what is the C rate and all, which I think you might be more curious to understand, but you would come across those items of C rates and etc. in the next coming slides. So let us now stick to the driving factors of the cell. So also the life cycles are defined at continuous C rates only. So which is a standard C rate. Life cycle is always designed at a continuous C rate, which is like you're not abusing the cell too much. It's a safe operating condition. It's continuous C rates are always the safe operating conditions, and life cycles are always defined at the continuous C rates only, and also at optimum operating temperatures. So this is how a cell is defined at. So when the cell is rated at 0.5 C or 1 C rate, the life cycles say are 3000. That means if you're going to charge and discharge the cell at 0.5 C or 1 C, then only you'll get 3000 life cycles, or not, you will not be able to get those kind of life cycles at all. So that is how the life cycles of cell are arranged. And then one more important thing is vehicle fitment, space and location. So the battery packs on high voltage battery packs like trucks, cars, etc., they can be mounted on the chassis, they can be mounted on the rooftops, they can be mounted anywhere. So knowing where that location is, how that placement is going to happen, how are they mounting the battery pack is something very important to know, because that will give you an idea of what would be the vibration loads over there, what would be the kind of environment that's going to be, like it's going to be too much heat, because if it's on the chassis there will be a lot of radiation coming from the roads, so your pack is going to experience extreme load conditions, not just the internal heat generation but also from the road radiation. If it's on the rooftop, you will be absorbing all the heat that is coming on the top of the vehicle. So that vehicle location is also where the battery pack is mounted. Its location is also really important to know. And then we have vehicle fitment space. As we discussed during the form factor slides, we know different cell form factors have different advantages and disadvantages. When we say about vehicle fitment space, now as we discussed on the form factor slide where we have cylindrical cells are usually smaller in size and there's a lot of flexibility in arranging them. But whereas when we have pouch cells, prismatic cells, they are bigger in size. So that is something where it becomes very important to choose the right cell depending upon the vehicle fitment space, what is the dimension of that available space available, and whether you can accommodate all the cells in that space or not. Remember, it's not just the cell which you'll have in a battery pack. You'll have a lot of other components, like you'll have cooling plates, you'll have BMS, you'll have a lot of contactors switching air over there to prevent the battery pack from high currents, high inrush currents, etc. So it's not the cell which is going to be in the battery pack. There are a lot of other components in the battery pack. You'll have wiring lines, you'll have voltage sensors, you'll have current sensors placed, you have power contactors, etc. So it's important to consider all those things and then you decide on the cell so that you have a proper vehicle fitment when the whole battery pack has been designed. I have a case study example on how the cell has to be selected, how it has to be derived from the specification of the battery pack. So without you have a specification of a battery pack, you cannot choose a cell. So it's important to understand the specification of the battery pack very much. So now we'll understand what is the case study for cell selection. So here we have a requirement of battery pack which is 630 to 640 volts, 200 Ah. And we also have C rate, which is charge and discharge rate current requirements, which have been split into two, which is continuous and peak charge rates. So when we say continuous charge rates, it's basically for a very small amount of time, which is like constant speed, which is a standard current during charging or discharging, which happens for a very long time. Whereas peak rate is specifically for a very small amount of time, like 1C or 3C or 2C, which is done for a period of 20 seconds, 30 seconds or 40 seconds or maybe 1 minute, not more than that. So that is one of the reasons why the cell delivers high currents for a short period of time, but when that happens for a longer period of time, the cell deteriorates quickly. So that is what cell selection is based on. Like, it is important for you to, for everyone who is working on this, to understand what are the continuous C rate requirements and what is the peak C rate requirement, like 1C, 2C, 3C for 30 seconds or however it is. So this is something which has to be evaluated. And then we have battery pack space available, 1.7 meters and 1.75 meters and 0.3 meters height. So let us get back into C rate requirements for some more time and understand what is it. So when we say continuous C rate, 0.5 C charging and 1 C charging, which means when you are charging the battery pack at 0.5 C is like 0.5 C times of 200 Ah. Like you have a battery pack of 200 Ah capacity and you are charging it 0.5 times of it, which is 100 amperes. So when you are charging the battery pack of 200 Ah with 100 amperes, the time taken would be 2 hours. Whereas if you're charging the battery pack of 200 Ah at 1 C, which is 1 times 200, which means you're going to discharge it at 200 amperes and it's going to take 1 hour for that. So it's all matter of 0.5 C or 1 C. If you're going to charge it at 0.5 C, it's going to take 2 hours, and if you're going to discharge at 200 amperes, it's going to be discharged in 1 hour. Similarly, the same is the case with peak charging. When you're going to charge it at 1 C, that is for a very limited time, say 30 seconds. That means you're going to charge it for 200 amperes within just 30 seconds of time. When you're discharging at 1 C, charging at 1 C is not a problem. But when you're discharging at 3 C, that is for 30 seconds, that is where you need to understand how this is going to function, how the cell is going to work. So that is something which you'll have to understand from the cell point of view. And then yes, we have the space availability, which is length is 1.7 meters, 1.75 meters width and 0.3 meters height. And then the whole pack has to be something around 900 kgs. So that is the weight requirement of this whole battery pack. Now another important part is like operating temperature. The battery pack must be operating only between minus 20 degrees to 55 degrees. Since the cell while charging and discharging generates a lot of heat because of the ions, electrons movement, and the electrochemical reactions keep on happening. It is very important for the cells and the modules to keep with the optimum temperature. And that's how you need to also decide on the cooling technique which is needed for keeping the cells within the optimum temperature. So that's how your cooling technique is also decided, which is basically your active cooling for the high voltage, because these are high voltage packs and high capacity packs which are operating at 200 amperes of discharge and 600 amperes for 30 seconds, which is too high. So you need to have an active cooling for this, which means active cooling is like you have a cooling plate where a water flows throughout it continuously so that the heat generated by the cells is always taken out. And then you have the location where it is going to be mounted. So here it could be either on the rooftop or chassis, and the life cycles that is to be achieved is 300 life cycles. So that means 300 cycles of charge and discharge at a continuous C rate condition, which is 0.5 C and 1 C discharge. So how do we select the cell? So here is a cell specifications which we have selected. So there could be a lot of cells, so that is something which we have a lot of database, and you could also find out different cells which are available. So when we select the cell, we have selected a prismatic cell which is LFP cell. And how do we know that? It's from the voltage over here, which is a typical voltage of 3.2 volts. So we have a cell which is 3.2 volts and it has a capacity of 105 volts. So we have chosen the cell, and when we choose the cell, we can also determine what is its voltage, what is its maximum voltage, what is its minimum voltage. So basically this is a cell specification sheet which we have figured it out, and from this cell specifications we need to match what the battery pack specifications are. Now if we see a typical voltage of this, which is 3.2 volts, we can see that if we put 200 cells in series, it would match what our battery pack requirement is, which is 630 to 640 volts. We could go there now. If we see, the requirement is 630 to 640 volts and 200 Ah. So that is a requirement. So for us, if we have 200 cells in series and 2 cells in parallel, we are going to match the requirement. So the voltage and capacity requirement are met. Then we go to the continuous current, which is charge and discharge. So the requirement for a continuous charge current is 0.5 C and discharge continuous is 1 C rate. So here we have met that continuous C rate conditions also. Now we'll see what a peak charge current is. It is 1 C rate and peak discharge is 3 C rate. But we have a conditions over here which says it's based on temperature and SoC. So what does that mean? We'll go and refer what is that based on temperature and SoC in the next slides. And then once we have this condition met, the other important part is going to be the operating temperature. So we have to maintain the whole cell and the battery pack within the operating temperature of -20 to 55 degrees centigrade. So even the battery pack requirements calls for the same. The cell requirement also is the same. Typically, mostly the lithium-ion cells are always operating between -20 to 55 only. So that is something you'll find it common everywhere. And the life cycles at 100% SoC is something which you can get 3500 cycles. So usually the requirement which we saw was like 3000 cycles. But here we can get 3500 cycles at continuous series conditions, which is kind of, we have met that as well. So when we see like the whole cell voltage window, it is from 2.5 volts to 3.65 volts. We can understand that the usable capacity is 106.5. But over here, see that the recommended SoC window is from 10% to 90%, which means if you do not use the cell from 2.5 to 3.65, that means you will not use the first 10% and you will neglect the last 10%. Then you'll have a little bit reduction in the capacity. So which means when you are always operating from the whole voltage window, from bare minimum to the whole maximum, you will always have stresses. So that is common everywhere. If you're going to use it to the full capacity, the system which you'll be using, any system, be it your mobile or a bike, anything, if you're always going to operate at higher thresholds of it, you're going to deteriorate the system much faster. The lives of the whole system gets affected. So that is something which you will have to consider. Like over here they have said the recommended SoC window is 10% to 90%. So that is something which you can consider or not, or you need not follow the same. You can make your own. Instead of 10% to 90%, you can start from 5% to 95%, which means you are still reducing the stresses which we would have. Like you have reduced the 5% stress at the lowest level and you have reduced the 5% stress at the top level. But literally this is something which is used everywhere to limit the operating voltage window. So basically the ends of the voltage are never touched. The cell should never see the ends of the voltage. If you allow that, you are still going to get the typical capacity, but the life cycles could go for a toss because you would deteriorate the cells much faster. So the selected cell over here seems to be much appropriate when we consider the major parameters like C rates, where life cycles play a very vital role. So it is something which you have to consider. And also the dimensions of the cell, which is like 130 or 36.7 and 200.5 mm height. So assuming that this is the right fit, this could also fit into the whole battery pack with these dimensions. You will have to do a rough calculation over here and see whether you can fit 400 cells, like 200 cells and 2 cells, which gives 200 into 2, which is 400 cells. See whether you can put 400 cells in that pack or not. That is something you can do a rough calculation and you can figure it out. Yes, it can still work out. So that's how you arrive at this cell. Now, we talked about dependent on temperature and SoC percent. When we talk about peak charge rates, we talked about that. Now, what does that mean? What does that peak charge rate mean when we say it is temperature and SoC dependent? That is what we saw in the previous slides, that the cells are based on temperature and SoC, which means that a cell certainly has a capacity of delivering or absorbing the current at high C rates. But it is dependent on SoC percent, which is nothing but the state of charge and the temperature of the cell that is needed at the time of delivery. Over here, which we have SoC percent on the x-axis. Over here, we have 100, 90, 80 and so on going up to 0. And then we have temperature on y-axis, which is from 55 degrees reducing to 0 degrees. But over here, you might have observed one interesting thing, that is, for charging, you can see the temperature is from 0 degrees to 55 degrees. So this is how the charging works. So during charging, lithium ion cells are not great when it is below 0 degrees. So at below 0 degrees, you do not recommend the cell to charge. You either use heater plates, you heat it above 0 degrees and then you start the charging. That is what the lithium ion cell chemistry has a disadvantage in charging because most of the lithium-ion cells have electrolyte filled, and those electrolytes, when they are freezed, the ion movements become quite difficult. So that is how you say, like, below 0 degrees, lithium-ion cells should not be charged. So that is how it is. Now, when we get back to this peak charge rate characteristics which is dependent on SoC percent and temperature. Over here we have seen like in x-axis we have SoC, y-axis we have temperature, and if you refer the first one, like the 55 degrees line, when it is at 100% SoC, 90% SoC, what is charge? Like if you have a vehicle, you have connected the charger and you're trying to charge it. That's what the charging is. So when you have at 100% and 55%, you have connected the charger, literally do not take any charge because you're already at 100%. But when you're at 90%, it takes only 10.5, and that goes on continuing up to 60 degrees. So till 60% SoC at 55 degrees, your cell would only accept 10.5 amps of current, which is just 0.1 C. And when it is from 50% to 0% SoC, your cell will accept only 21 amps of current, which is 0.2 C. So you have a capacity of 105 Ah, but the cell is having 0 SoC. There is no charge in there, but it will still take 21 amps of current only, which is 0.2 C. Why is it? It is mainly because of the temperature. Because your cell is at very high temperature, 55 degrees, if you charge it even more, the temperature is going to hike even more. So this is certain condition which you will have to program in the BMS as a safety precaution, saying that if your cell is at 55 degrees, you will not be charging it more than 0.1 C or 0.2 C. If you do that, you are going to raise the temperature of the cell, which is going to lead to some disastrous effects after that. And then after, if you see 50%, so these are all the cell characteristics. This is all coming from a cell testing window. So a cell has to be extensively tested, and this are something which has to be found out. What are the limitations of the cell? So now see, if we want to charge it, the requirement was just 1 C. And if you see at 25 degrees, when the SoC is at 70%, you can charge the cell at 3 C. This is huge, this is great. But it also has to be at a 25 degree temperature. And if you see at 45 degrees, you can charge the cell when it is from 50% to 0% SoC, you can charge it at 105. But the moment you cross 50%, you should not allow the cell to be charged at 1 C rate. You should allow the cell to charge at 0.5 C rate. That is the limitation of this chemistry, or the limitation of the cell. That means the cell is capable of doing that up to a certain limit, or a voltage, or a SoC percent, or a temperature window. So that is something which you have to program it in the BMS, saying these limitations, like at 25 degrees, and if the SoC is lower than 80%, then only I will be charging at 3 C rate. Or else if it is increasing, the moment it crosses 70 degrees, I'll charge at 1 C. The moment it crosses 80% SoC, I'll charge it at 0.5 C. This is something which you have to pick these tables. This could be a lookup table for you, and you can program your BMS accordingly, which would make the whole battery pack function accordingly. So that means if you have a charger and the state of that battery pack is at 55 degrees and you have only 30% SoC and you want to quickly charge the cell or the battery pack, you can charge it at only 0.2 C, which means you will have to bring down the temperature to certain 45 degrees or 25 degrees to charge it even more quickly. So that is the action which you have to take, and that is dependent on the BMS, how you program it. The more and the more better you program the BMS, the more testing data you have, the better would be the result coming, the better would be the operation of the battery pack. Now this is for the peak charge rate. Now the similar is something which is for the peak discharge rate. So over here, if you see, it's interesting that the temperature has now gone from minus 20 degrees to 55 degrees, whereas charging was from 0 to 55, but the discharge is from minus 20 to 55. So up to minus 20 degrees or sub-0 degrees, the discharging can happen. That is the gist of lithium-ion cell chemistry. So lithium-ion cells can actually discharge cells at minus 10, minus 20 degrees. But one important point over here is, if you see at minus 20, your C rates have fallen way below. So it is till minus 10 C also it can deliver 1 C. But if you see at higher C rates, like at 100% SoC, so it is opposite of discharge. When you are charging the cell, if it is 0%, you should see the first 50% has all higher values and the next 50% has lower values, because your cell has already been charged up to a certain amount, and when it is filling up, which means, for example, you have a glass and you are filling it with a filter water, you are filling it. So what do you do usually? You keep the tap open until it is getting filled 50%, 60%, 70%, and the moment your glass is almost about to fill, you will put your hand on the tap to close it slowly. So you will allow the water to slowly fill and then you close it. So this is doing the same. This is your charger which is doing the same functionality. So when the battery is fully empty, you are charging it fully, and when it's slowly nearing to its 100%, you are going to give the charge slowly so that you will reach the 100%. So it is the same. But whereas when it's a discharge, what happens is you are already at a very full level. You have full amount of charge, and when there's a tank which is fully loaded with water, and when you open the tank, what happens is there's a huge rush of water coming out. It's the same. When you have a full charge cell, no matter you're at 25 degrees, 55 degrees or 10 degrees, the energy or the power which that can be drawn from a cell is huge. So that can be reflected over. You can see for a 55 degrees, when the cell is at 100%, 90%, 80% SoC, you can get 5 times, 5C of the current is coming up. But remember, this peak C rates and peak discharge rates are for limited time, that is 30 seconds only. So you'll get 5C for 30 seconds, and then from 70 to 60% SoC, you'll get 4C. And then from 50% to 10%, it's slowly reducing, 3C, 2C and 1C. Similarly, at 25 degrees, you'll observe the same. Now, there is a change over here, 25 degrees to 55 degrees. If you see, the 5C delivery can be up to 60% for 25 degrees because your cell is at a very good optimum temperature. Whereas at 55 degrees, that is the top point of the optimum temperature, there is some limitation applied over there. So over here, there is another thing. If you are reaching to the nearest lowest SoC, you should not be drawing more power because you will be abusing the cell. That's the reason your C rate reduces as the SoC reduces. But the same is opposite in charging. If you're nearing to the 100% SoC, you should not be charging at higher C rate. You should reduce your C rate so that you don't abuse your cell. So this is something which you have to take care. So there's a C rate. When you are nearing to 100%, you charge it slowly. When you are discharging and you are nearing to 10%, 0%, you discharge with a lower current. So that is how you program your BMS accordingly, so that you don't abuse the cell much. You are operating the cell in a very good optimum operating zone, so that there is no abusing of the cell, which can give you the life cycles as expected. So till now we have selected the cell depending on peak C rates, etc. Now we'll understand what is the cell selection based on life cycles and SoC. So when we see the first graph, we have life cycles 0 to 4000, and we have capacity retention window, which is 0, 60% to 105%. So here, as per the data sheet which the cell says, which says that by the end of 3500 cycles, you'll have a capacity retention of only 82%, which means if you use it further, your capacity will fade out and you'll be losing a lot of capacity. You'll not be able to use the complete capacity. So usually in EV also, you stop using the cell when it reaches 80% of capacity retention, and then later on you can use it for any of the storage applications. But one important thing that you wanted to consider over here is, when you have 3500 cycles at a capacity retention of 80%, which is when you have used the cell for a complete voltage window, 2.5 volts to 3.6 volts at a standard operating condition of C rates, which is 0.5 C and 1 C discharge. So at that rate, if you are using the whole voltage window, 2.5 volts to 3.6 volts, this would give you 3500 cycles. But if you also remember, there is a certain recommendable window which is 10% to 90%. That is what a recommended window was given by the cell manufacturer. So if you do that, what you would do is, this stress, the box which is the red box, is something has been highlighted so that you limit the cell voltages. But what would happen is, every capacity available about 3.4 to 3.6 volts is taken away. You will not be able to use that. And all the capacity which is from 2.55 to 2.5 volts is all gone. You cannot be using that also. So which means you are going to limit yourself to the 2.55 volts to 3.4 volts, and essentially the capacity lost is lost. So that is something which you will have to understand while doing that. So if you have a cell which is like 106.5 capacity, AH capacity over here, and by limiting the cell voltages to 2.55 to 3.4, there is some percent of capacity being lost. But your need is 200 AH. You have selected a cell of 106.5 Ah, which is typical, and minimum capacity is 105 Ah. So when you reduce this kind of voltages like this, you lose some percent, like 5% or 10% of the capacity, which means if you have two cells put in parallel, which is 105 Ah into 2 becomes 210 Ah, you are already 10 Ah higher than what you need. So by limiting these voltages, you will lose some capacity, but still you will have your required 200 Ah capacity there. By doing such kind of selection of a cell which is slightly higher than what is required, what you can do is you can always limit your voltages to a recommendable SoC, like 10% to 90%, so that even though you lose your capacity, you are still meeting your required capacity. And one major advantage of that is your life cycles are going to still increase, because this life cycle of 3500 is from 2.5 to 3.6. But definitely if you're not going and meeting the ends of the life cycle of the voltages, your life cycles are definitely going to increase much more. So this is an advantage which you could do. This is something which is in your hands. You can program the BMS accordingly, saying hey, you do not allow the charge up to 3.6 volts, and you do not allow the discharge to 2.5 volts. You are going to limit over here. So the BMS would act accordingly. So by doing this, you are not allowing the cell to be stressed at charge condition and discharge condition, which eventually would increase the life of the whole cell, whole pack, etc. So this is something which you have to do it, and yes, you have to slightly oversize the cell, so that even though by doing this kind of cutoffs there is some capacity lost, but still you are meeting the capacity which is needed for the battery pack. So this is something which you have to see. And also I would like to highlight a little bit over here, which is for the second graph. So if you see, there are different C rate graphs, 0.3C, 0.5C, 1C up to 3C. So if you see the green line, which is for 3C, and if you're discharging the cell at 3C, you see that you end up quite before 105 Ah. And if this is done quite often, you'll end up in loss of capacity. This is because the time required for the electrochemical reactions to happen inside the cell, you're not allowing that amount of time. So which means the capacity or the reactions are incomplete, and if this gets continuous again and again, the half reactions are still half, and you're doubling that to happen, and that's how your capacity retention, the usable capacity, all falls down. Whereas if you see the purple line, which is 1C, that goes and ends exactly at 105 or even a little bit more, which means all the reactions, all the ion movements have all been transferred from cathode to anode and anode to cathode, and all the reactions are complete, which means you'll get higher life cycles, the required capacity, etc. So it is really important to see that the 3C discharge is limited for 30 seconds. If you're going more and more and more, you're going to lose your capacity. Discuss on the process of flow for the pack designs. Now, since we have gone through a lot of understanding on the basics of cell, module configuration, series and parallel combinations, C rates, life cycles, voltage windows, etc. Now let us focus on what is the process flow for the pack. So step 1. Since we have seen a case study on how the battery pack requirements look like, and from the battery pack requirements, we need to choose the right cell that is to be selected for the application. So this application is mainly for bus and car, and it's a high voltage application, and we have to choose it accordingly in the right way. And then after the selection of cells, we need to consider the battery pack voltage and capacity, which we have done, and then we are going to combine the cells in a module in different series and parallel combinations. But over here, when we have to make modules, we'll have to pay more attention that all the modules are of same voltages and capacity, so that for example, if we have to get a 60 volts as nominal voltage with 100 Ah capacity, the preference would be like we'll have to connect 4 modules of 15 volts and 100 Ah each, so that we'll get a 60 volt. So that is something which has to be taken care of. When we make a pack, all the modules should be equal, and yes, the module consists of several cells which are to be connected in series and parallel, and that has to be rightly chosen. So the most important factor for this whole pack, which is the cooling design. Now we have modules in place, we have cell configuration in place. These cells are of high capacity, high voltage applications, so they dissipate a lot of heat because there are a lot of charging and discharging happens, there's a lot of heat being generated, and with such amount of heat being generated, it's very important to extract the heat. Therefore, the cooling design calculations has to be intact. So which means, as per the rise in temperature, the cell which generates heat has to be extracted through a right cooling mechanism. And for high voltage, preferably active cooling is used, where we have a cold plate. As we have talked earlier, we have a cold plate and there is water flowing through the cold plate, and the cold plate extracts the heat accordingly. So the flow rate has to be right, the material used has to be right, the module to cold plate contact has to be the right way. So all these things are playing a very essential role in choosing the right cooling design calculations, etc. And apart from that, we have a lot of electronics, wiring harness designs. So when we say electronics, we have BMUs, we have BCUs, we have cell-to-cell interconnections, which is through bus bars. And there's also a very important part, like when we have a bus bar, the contact resistance has to be as low as possible. That means the weld joint has to be good. So that is one. And then we have wiring harnesses, and which means we have wires of different diameters, lengths, etc. And we need to see that there is no voltage drop, there is no overheating of the wires. We need to choose the right wire appropriately. And then one tip over here is, like, the pack is usually a combination of lot of modules connected together. It could be in series to achieve the final voltage, or it could be in parallel connections or module. Usually we should be avoiding the parallel connection to avoid any string controllers need, etc. So that is one tip which we could always see, that let us make sure that the modules are always connected in series, so that we keep the parallel combination of the cells at module level only. So that is something advantageous to us when we go at a pack level, so that we only have series combinations, which would make the whole life easy. Instead of 10 modules, we series it, and then we have another 10 modules, we series it, and then we connect them in parallel. It's going to be a huge confusion, and it's not preferable when we do a bulk production in such way. So these are the 4 steps which are to be considered when we do a pack design. How do we define the process for the whole pack design? Now we'll go back a little bit into module design considerations. So here we'll understand, since we have 3 different form factors, cylindrical, pouch and prismatic cell, which are arranged in series and parallel combinations, we'll try to understand what does each of them have. So over here, the first one is for a cylindrical cells. So here we have cylindrical cells which are arranged in series and parallel combinations, where we see a cylindrical cell with a capped side, which is this one. It's a positive side, and we have a plane area which is negative side. I believe cylindrical cell is something which you might have seen daily almost. So this capped side is usually the positive cell. So if you see the next image, we see that there are a group of cells which are placed with flat heads on the top, and also there are a group of cells which are placed with capped heads on the top. So which means they are placed in zigzag arrangement. So which means for series combination, you need to connect one cell of a positive to the negative of another cell. That is how you get a series combination, like positive of one cell is connected to the negative of another cell. Here is what that we see in the image, like the groups have negative side facing, and when we have positive side facing on the top, which are put together. So which means we are going to connect them through a nickel bus bar. So the bus bars usually used for cylindrical cells are nickel. It could be a copper or coated with nickel. So these are the bus bars which are used. So here if we see, we have a common group cells. We have 16 cells like this. We have 16 cells for the positive, which means here the 16 cells are in parallel. So which means we have 16 into whatever be the capacity, like 16 into 1 Ah cell, we have 16 Ah, which means the pack capacity becomes, or the module capacity becomes 16 Ah. And since we have 1, 2, 3, 4, 5 cells, a 5S combination, like we have 1S, this is 2S, this is 3S, this is 4S, and this is 5S. So this whole of them are arranged in 5 series combinations. Each string or each group has 16 cells, and 16 cells are of the positive side are also arranged on the same side. And now like that you have 5 groups, so that you connect one group to another group becomes 1S. When you connect second group to the third group, it becomes 3S. Next it connected becomes 4S. Then when you connect it to the last group, it becomes 5S. So you have 5 cells or 5 groups connected in series, with each group having 16 cells connected in parallel. That makes it a 5S 16P configuration. This is how a module has been configured. That means over here, let's take a typical capacity. We have a cell which is from 3H to 5H capacity, and form factors are anything 18650, 21700 or 32600. So as I was mentioning, 18650, the first two numbers over here, the first two digits represent the diameter of the cell, and the next two digits 65 represent the height of the cell. So the capacity of a single cell is smaller, so we have several cells have to be connected in parallel, which is to achieve a 200 Ah we need to have 5 Ah cells of 40 numbers connected in parallel. So this is how you get a cylindrical cell in parallel combination. See, just imagine 16 cells connected in parallel to get the required capacity. So this is how you make a module. You put all the cells where you wanted to get the capacity, you put all them in parallel first, and that becomes a string. You connect all the strings, positive, negative of each one string to another string with the positive and negative of those string. You get a series combination. So this is how a cylindrical cell module is designed. So now we see exploded view. So over here, if we see an exploded view of a cylindrical cell, we have a cell holder or a heat sink. Usually a heat sink is used so that when the cells go inside, all the heat is extracted well. So you have cells going into the heat sink, and then you have cell to cell interconnection. These are the nickel bus bar used, these pink ones. These are the nickel bus bars used. And then over here, this brown portion is something that acts as an insulator, so that these bus bars do not touch the cell body, because the cylindrical cell casing is a metal body. It's a metal can, so that you insulate it over there first, and only the required portion is exposed, and that is where you connect the bus bars and weld it. And then you have a sealing gasket, so that there is no ingress. Once you put the sealing gasket and then you put the enclosure, there is no water or any dust entering into this whole pack. And then you have a wiring harness. So this wiring harness could be a PCB or sensor wires, voltage wires, etc., anything, so that you connect each sensor to each cell, and then you monitor the voltage or temperature of the whole unit. And then you have electrical isolation pad, because there is current carried everywhere. You need to isolate all the exposed body of the cell, so that this is the battery pack enclosure which is in contact with the cells of the bus bars. That portion has to be insulated well, so that when somebody touches the battery pack externally, the current is not flowing through that. So you need to isolate all the parts, or you need to give a proper electrical isolation to all the electronic parts internally for the battery pack, so that there is no current or open circuit voltage flowing through the enclosure of the battery pack. It is common for anything. It has to be common for cylindrical cell or a pouch cell or a prismatic cell, that this is some care which has to be taken very appropriately.
Or else, if there is any floating current going on, there should be shocks to the people sitting near to it or people touching it.
So that could lead to electrocution. And now we'll discuss on pouch cell. Now the earlier one was cylindrical cell, where we saw a lot of cells connected in parallel, which is called a string. Then such strings are connected in series, like positive of that string is connected to a negative of the other string, and then that becomes a series combination. Just you saw how many cells are involved there. Whereas when we see a pouch cell, it is quite easy. Now if you see, there are just 4 to 5 cells, and this each cell capacity itself could be 20H to 65H. But what happens is in prismatic and pouch cell, as we discussed, that these cells tend to expand over a period of time while charging and discharging. So here is what we see, where we have a pouch module, where we have more parts over here. We have a metal plate, we have a bottom plate, we have a thermal insulation, right? These are LTO cells, and there are a lot of BOM parts that get added to this. And though the capacity of this cell is bigger when compared to a pouch cell, maybe the number of cells needed would be less, but the number of other parts needed to assemble would be more. So one thing is, in this pouch cell, we use metal plates in between. So these arrows which are there, we put metal plates over there, which is preferably aluminium, so that the heat generated, because there is a lot of flat area lying over there, there are vacant spaces, the metal plate we can insert over here, so that the heat can be dissipated from the cells, which acts as a heat sink over there. That is in contact with the bottom plate, which could be a passive cooling system. So all these lines are basically the fins. So you put a metal plate which is in contact with the cell body, and that metal plate is in contact with the heat sink below, so that all the heat which is generated by the cell is conducted to this metal plate, and that transfers it to the passive cooling system, which is the heat sink below. And that's how you take away the heat as much as possible. So whenever you're charging and discharging the cells, the cell will generate heat, And to avoid overheating of the cells, you dissipate the heat in this way. So you can put metal plates, you can put any good thermal conductive materials, like you have thermal foams, thermal pads, thermal paste, anything you could put to dissipate the heat. But what happens is, if you do charge and discharge, these pouch cells tend to expand a lot. And when such expansion happens at a certain point of time, the cell bulges a lot and it could lead to explosion. So it is very important to hold the cell intact by applying pressures on both the sides. So you can put a pressure plate over here, you can put a pressure plate on the other side, and you fasten it tightly with a pressure plate so that all the cells are put together. You're tightening them so that whenever there is expansion and contraction, the cells are not bulging as much as, because there's already a pressure acting, so the cells do not tend to expand a lot. So this is something which you need to consider, this complexity. There are a lot of complexities, but you need to do the right selection of design to make it safe. But still, there are certain advantages of this pouch cell, like you have higher energy density, the volumetric energy compared to prismatic cell is higher, and also because of its larger capacity cells available, the number of cells needed for parallel combination reduces a lot and compared to cylindrical cells. So this is something which you need to consider while making a pouch cell module. So and also what happens is, when you connect the cell to cell, the contact resistance by using a bus bar also has to be made sure that the welding is right, the welding is proper. So that is a challenge in cylindrical cells, because we have a lot of cells and you have a lot of bus bar to cell connections, and in such cases the welding has to be right, or else there could be a lot of contact resistance built up. And the same could be with pouch cells, but because the cells are less, you don't have much contact resistance added up because of less cells. So that is the advantage when you have with pouch cell. The same case when you see a prismatic cell. Prismatic cell over here is a little bit different. Now, if you see a pouch cell, which is very thin. So there are certain difficulties. When you have a thin pouch cell, if you want to extract heat, only this area, this flat area is the only portion available for you to extract heat. Because if this certain thin portion, this is like 12 mm or 15 mm, not more than that. So there is no way where you can extract heat from the side or from the bottom. But unlike that, you have prismatic cell which has a decent amount of thickness. Usually prismatic cells have a thickness of 28 mm to 30 mm or even more. It depends on the capacity of the cell. The bigger the capacity, you could see that the thickness of the cells are a little bit higher. So when such thing happens, when you have prismatic cell, just see the way the thickness of the cell is. You can directly put all the cells over here in a module, and you can use a side area for extracting the heat. So this is one great advantage that you will find with the prismatic cell, that you will have sufficient area. In fact, you don't need to put metal plates in between, and also find a path that is touching the external side plates so that you conduct the heat. So all that are gone, all that are not needed with the prismatic cell. The construction of the module becomes quite easy and becomes quite effective, so that you have wide areas of thickness where you can extract heat as much as possible. That is one advantage you'll have with the prismatic cell module. But followed by some advantages, there will always be certain disadvantages. Now the prismatic cell has higher capacity, and these cells are to be connected. At least the parallel connections are gone, because you have higher capacities, you don't need to connect them in parallel. But the series connections are something which you'll have to do, ultimately you'll have to do at any point of time. But when that happens, as you know, the prismatic cells over here have different kinds of terminal tabs, positive and negative tabs. You can have a prismatic cell with tab welding option, or you can have a prismatic cell with a internal threaded option, or you can have a prismatic cell with tab with a screw. So when such kind of prismatic cells are used, you will have to connect the bus bar through nut and bolt. And with nut and bolt, there are a lot of tendencies that through vibrations or mechanical shocks they can get loosened, and when they get loose, the contact resistance builds up and there will be hot spots formed over there. Usually also, when we have a cylindrical cell or pouch cell or prismatic cell, when you run a thermal analysis, the bus bar tabs or the top portions where the current is being extracted, those are the hot spots. And when you have such not good joint between the bus bar and the cell with a nut and bolt, that can increase the contact resistance even more. So that is something which you have to consider when you have a prismatic cell in use. You will have to follow the right torques, right amount of force required for fastening the bus bar with nuts and bolts. So that is something which you'll have, but followed by there are a lot of advantages considering the thickness of the cell. Here you can put thermal pads below on the sides and extract the heat directly from the cell to the heat sink or enclosure. And yes, you would also need a pressure plate over here, even though there is a aluminum can for a prismatic cell, but still you need some pressure plates so that the slight expansion or anything which can happen is arrested properly. Now we'll understand what are the different role of components in the battery pack. So in a battery pack you have different components which we discussed. So this is in general. So we have components like we have when making a module, like we need cell holders, which is basically to hold the cell. And when it comes to a pouch cell, this HCP we call it a heat carrier plate. So which is nothing but a metal plate which we saw in the earlier slide. So that becomes an integral part of the cell holder. So this becomes a unit which usually a cell holder can be ABS material, and HCP is a heat carrier plate which is used for dissipating of heat from the cell. It is basically aluminum because aluminum has lightweight and also it holds a good conductivity. So aluminum is usually used as a heat carrier plate for dissipation of heat from the cells. And then we have thermal foams.
Why do we use thermal foams over here? Usually these thermal foams are something which can expand or contract, which is known commonly to everyone.
So when the pouch cells are used, the pouch cells during charging and discharging, they also expand and contract. So when such things happen, there is some gap or void which forms. So when you use thermal foam between cell and a HCP, whenever the cell contracts, what happens is that extra space which it creates is going to be filled by the foam. And when it expands, since foam has a capability of taking the deformations, the foam takes over there. So this foam which is used has to be calculated, like you calculate such that the foam is compressed to only 30% or 40% and you still have that 70% of elongation left with the module, so that whenever the cell is expanding and contracting, the thermal foam takes those changes in the dimensions or thickness of the cell. So now we'll understand what is the role of components in the battery pack. This is basically a cell block. We have a lithium-ion cell and we have a thermal pad which is placed on it. And this is how it can be a foam or it can be a pad. And then we have a cell holder which is coming on top of it. So this is how a lithium-ion cell forms. So we have all of it together. So now we have a prismatic module. So this is the same module which we have considered the cell of 3.2 volts 105 Ah. So with that cell we have made a prismatic cell module with the same prismatic cell, and now if we remember, that cell was of a dimension called 130.3 mm and the width was 36.7 mm and the height of the cell was 200.5 mm. With that we have arrived at a module where each module will require 20 cells, and that means when we put the cells in a 10s2p configuration, that cell each of 3.2 volts, when 10 cells are connected in 10 in series, will give 32 volts. And then when we have 2 cells in parallel, it would give a capacity of 210 volts, which means we have 20 cells connected in 10s2p configuration. Then the module of each would be 32 volts 210 Ah with a dimension of 790 mm, 136 and 220. So this is how we arrive at a prismatic module, and connecting all these modules in series combination would give the required pack level. So one important part over here is, you will be surprisingly if you do a small math directly over here, which means you have 36.7 mm along the width, which is this, and you're putting 20 cells over here, your math would not tally because you're putting 10 cells, 20 cells into 36.7 mm, it would not give you 790. And similarly, when I just said the width of the cell is 130.3, but over here I have arrived at 136 mm. You'll be confused, how is this happening? It's not a mistake, it's not an error. And again, when I said height of the module is 220 mm, but the cell's height is 200.5. So where are these extra dimensions coming from? So these dimensions are coming from the extra BOM components which are involved in the prismatic module. As I said, this does not only involve cells only. The prismatic module consists of end pressure plates like this. We have end pressure plates, we have side plates, we have thermal pads coming in between, and then we have top cover for insulating the whole bus bars. We have bus bars coming in. You should be using cell holders for each cell. Well, there are a lot of other components which are coming into a module, so it doesn't just become the bare cells only. So there are a lot of other parts. So what are these? That we'll understand the calculations. So now from this slides we'll see what are the bare cell to module dimensions. So now we have module length, which is module length becomes 20 times of cell thickness, which is the thickness of the cell. That becomes the module length. So that means the thickness of the cell when arranged 20 cells together becomes the length of the module. But the module width remains the same. Module width is nothing but 1 times 130.3 is 130.3 mm. And the module height is 1 times 200.5 is 200.5 mm height. So these are the bare cell to module dimensions, but we have a lot of dimensions which are changing in this slide. If you see 790, 136 cross 220 mm, and we have 734, 130.3 and 200.5, it's different. So in the next slide we'll find out what is the difference coming from. So the module consists of thermal foam, which we have assumed to be 0.5 mm after compression. We have a cell holder which is 0.5 mm thick. We have a heat carrier plate which is 0.3 mm along the length. So when we put all these together, we have 26 mm. Module 1, which is 26 mm, is the extra module length which is coming when we consider all these thermal foams, heat carrier plates, cell holders, etc. And then we also have end plates which are coming. We have end plates, 2 numbers, each being 15 mm. That is the reason why we get 790 mm. The next one, module width. We have assumed 2 mm to be the width, which could be the cell holder and any other thermal foam used, and then that gets added up to the module width of 130.3, which gives us 132.3 mm. And then we have a busbar height which is of 5 mm, and we add up to the module height, it becomes 205.5 mm, and we put a cover on top of it which gives the extra 10 to 15 mm needed. So all these 5 mm, 2 mm, 26 mm are all assumed dimensions as per the design simulations. All these values would definitely change if a proper analysis is done according to the cell available. So these dimensions would change, and the analysis drives all these dimensions needed. So these are just for information how these dimensions play a major role in deciding the module overall dimension. Now we'll talk about the selection based on the sizes and volumes. So over here now we'll understand the modules depending on the different size of the battery pack available. How do we fit into that? Now we have a battery pack which is having a length of 1700 mm. We have a width of 1750 mm, and the height is along the Z axis, which is 0.3 meters, and we have 0.2 meters assumed, so I think we'll have sufficient space on the height. So if we see over here, now let us consider the volumetric efficiency of this whole thing. We have 20 modules, so the total pack volume is something around 0.89 meter cube, and we have a module volume which is 0.48 meter cube. So these are the module volumes which is available. So we have at least 60% of it still we have occupied, and we have rest 40% available with us. So those are the volume which has to be used for the other components. Like we have electronics, like we will place the BMU and BCUs over here. So then the green area over here represents all the contactors, power connectors, BMS, wiring harness used in this battery pack, and the yellow area over here represents the cooling hose pipes, the cooling line inlets, outlets, etc., which are required for fixing the cooling plate. And the cooling plate, mind you, would always be below the modules, so that the heat generated from the modules is taken away from the below portion. So that is the place where a proper contact has to be achieved between the modules and the cooling plate. So these are the selection. How do we separate the dimensions for the modules? How do we allocate the dimensions needed for electronics, etc.? It has to be at least 30% to 40% left, so that we can utilize that space for all these electronics, etc. Now we'll talk about what are the different requisites for having a robust pack. Now a robust battery pack should have certain qualities where it should be able to withstand vibrations and shocks. So to do that, that means it's not just the pack. this vibration shock must be such that the module, when it is designed, the module should also be sustaining such kind of vibration. So usually in India we follow AIS standards, which is calling for at least 3G load vibration. So usually when we need to do this test for transportation, like means if we are shifting the pack from one place to another place, there is a certain standard called UN 38.3, and that calls for vibration level up to 5G or 8G. So imagine what kind of engineering you need to put into so that the module and the whole pack is going to sustain such kind of vibrations. So this means that all the enclosures, modules which are designed, all the mounting which you would be doing of the BMS inside the battery pack, this would be subjected to a constant phenomena of vibration throughout when it's on the road, when it's on the train, or when it's being shipped, or when it is on the moving vehicle which is discharging. So anything, any loose contact, like any loose screws or anything, would make the whole pack stop, terminated. The BMS might terminate the whole pack because of any loose contacts or loose wires and all. So it is very important that when the whole pack is assembled, when it has to be assembled, the right torque values have to be used. One of the important consideration is whenever the screws are used for critical components like sensors and all, you could always use a thread sealant so that with the right torque, which would hold the screw well so that it doesn't loosen quite often. And then the most important part, the next one, is the good ingress protection. This is something very important, like all the enclosures must be properly sealed. Like it has to prevent water, it has to prevent the dust entry, as these battery packs are used for the buses, which could be rooftop or chassis mounted. There is going to be a high probability of dust and water, and imagine being at any of the packs in India with all puddles and water puddles and non-uniform roads. The pack is going to be subject to a lot of vibration, and with that vibration, if your sealing ingress is not good, sealing ingress just damages, and then you will have all the water and dust going into the battery pack, which could first deteriorate the performance of the whole pack, and then it could also lead to a lot of catastrophic failures like short circuit, etc. can happen. And then the next important part is the thermal dissipation of heat. So all the cells over here generate heat during charging and discharging, and that has to be effectively dissipated as much as possible so that they are operating at optimal temperatures. Therefore, you need to design a very good thermal loop always, so that thermal loop will help you to dissipate the heat. And what does the thermal loop consist of? It's just that what we decided, what we saw earlier, like it should have a thermal plate, it should have a heat carrier plate, there is a heat sink which has to be calculated properly. All these calculations should be done. So these are theoretical, but when you do it in practical conditions, you need to take care that there are no air gaps formed between the cell, heat carrier plate, etc. That is something which you need to take care while doing a thermal loop design for thermal dissipation of heat from the cells. And then you need to have a very good electrical isolation for the vehicle body. So there has to be no live current coming from the electrical parts like the battery pack especially. So you need to select the right wiring, and you need to see that all those wiring and all the current carrying wires and all are shielded as much as possible. As we saw in the exploded view of the cylindrical module exploded, we used an electrical isolation sheet where it will stop the bus bars in contact with the enclosure of the module. So that is how something you have to take. You can use any electrical isolation sheets, you can use silica sheets, mica sheets, or you can use any preferable coatings on the internal part of the enclosures so that they do not conduct electricity whenever bus bar or the cell is in contact with them by mistake. And then most important part is again the venting of gases, which is basically in case of cell failure, you need to vent out the gases as much as possible so that the pressure doesn't get built up inside the whole battery pack. And the pressure would definitely get built up into the battery pack because this battery packs are usually IP65 or IP67 sealed, and when such kind of pressure buildups with such sealing happen, it is very important to vent out the gases. So therefore you need to use breathing valves, vents for the battery pack enclosure. Whenever the temperature builds up above atmospheric pressure, this vents open up and they release the gases as much as possible so that the battery pack doesn't become an explosion bomb. And then communication. This is one of the most important factors for the whole battery pack. You need to have a seamless communication between the battery pack, which is the BMS, and which is the communication portion, and the vehicle control unit, where BMS would be translating all the information from the battery pack to the VCU, so that the vehicle constantly knows what is the status of the battery pack. If there are any errors, the VCU would immediately communicate and take control, saying that you terminate the battery pack, so that there are certain errors that has been triggered and you should not use the battery pack anymore. So such certain kind of communications happen between the BMS and the VCU. So this is the reference high voltage design pack, how it looks like. So as we saw, we have a lot of battery modules over here. There are like how many? 18 modules over here, and each module. So this is a slightly different design. If you see, the cooling plates are placed between the modules. So we have 1, 2, 3, 4, 5. We have 5 cooling plates over here. We have modules over here, and all the switch box and all the electronics are over here. This one of it is a battery management system. This is the lower housing system. So this is the low enclosure. So basically there would be a top enclosure coming over it, which will be fixing the whole pack, which would be covering the whole pack. So this is how a high voltage battery pack would look like. Just imagine a lot of modules, all the wiring harness coming from this goes into the switch box at the top. It's over here. So this portion is the controlling part of the whole battery pack. So this is how the high level components of a battery pack would look like. Continue with some of the role of the components in the high level battery pack when it comes to electronics. So the electronics used at module and pack level are like, for charging and discharge monitoring, we use BMU, which is called as battery monitoring unit, which is used at module level. Basically BMU and BCU are something which are used for high voltage applications only, because BMS would be limited with limited number of channels, whereas BCU and BMU would give that flexibility to use more number of cells in a battery pack, and it can eventually monitor it as a master BMS or a slave BMS. That we would discuss in the third week, but let's continue with this, how and each function of these components are like. BMU, it's a battery monitoring unit. It just monitors the cell, and all this information is transferred to the BCU, which is the battery control unit. And then we have BMS, which is a single board for low voltage applications. This is commonly used for battery packs which is less than 60 volts. And then for communication, we will be using a CAN based communication. This is one of the features of BMS, which is used for communicating with the CAN. So this is something which is common, which is of high importance in a battery pack to understand what is the status of the battery pack. And then for safety and control, we use precharge circuits. This is one of the unique feature which is used in high voltage battery pack, which usually consists of resistors and contactors. So this is to avoid the high inrush current which is coming from the battery pack, so that it doesn't damage the vehicle side controllers and motors when the ignition is turned on. So this is one safety feature that has to be included in a battery pack, and it is quite essential to do that. And we'll discuss about this in the coming slides. And other electrical and wiring components are like at voltage level, at module level, we have voltage and current sensors, which are used to monitor the current and voltage levels of every cell. So this voltage sensor goes and it is fixed on every cell which is in series connection. So it is to monitor, and all these voltage and current sensors go to the BMS. From the BMS, that is how when you program the BMS with certain voltage cutoffs, voltage limitations, you say instead of 2.5 to start, you'll start with 2.65 only. That is where this voltage sensor will play a role. So this voltage sensor senses the voltage of the cell, and the moment it reaches that certain set voltage, the BMS would take an action to start discharging or to stop charging and all. And then we have temperature sensors, which are also called as the NTC sensors. So these NTC sensors are used to measure the temperatures of the whole battery pack, wherever we have hot spots, wherever we have high temperatures zones forming on the module or at a pack level. The NTC sensors are detecting that, and that information is translated to the BMS, so that the BMS can take its action to stop operation if the temperatures are quite high. And then at pack level, we have current sensor. So this current sensor is something to understand how much of current is being drawn and how much of current is allowed to draw. And this current sensor is actually again in contact with the BMS to transfer the information continuously. If there is any high current coming up, and if the pack is not designed to do that, it will immediately send a signal to terminate. And we also have other safety monitoring device like manual service disconnect and high power contactors and high cables. So manual service disconnect is something which is needed to break the voltage loop whenever this is being serviced or whenever the big battery pack is being shipped. Whenever the whole work or maintenance work on this battery pack is done, the final assembly happens, and then this manual service disconnect is plugged in so that the loop is closed. So until that, the first thing to start before opening a pack is to plug out the manual service disconnect. This is just a plug. You can remove it easily and you can place it easily. So it is manual service disconnect, which also is one of the important component for servicing aspect. By now we have talked about different modules. What are the series and panel combination? What is the thermal loop design? What are the cell chemistries, cell form factors, etc. So suppose we have made a very good module. We have made a very good thermal design. Everything seems great. We have fit into the right place. We have placed all the components, etc. But what if the power cable is not right? Because ultimately the power to be drawn is through the power cable. If that is not done right, the whole essence of making the great battery pack goes in vain. So it is very important to also choose the right power cable for a battery pack. So now here we will understand why we need to choose the right power cable. So since the power cable would be the final medium through which the power is delivered, the power cable has to be selected that it can deliver 1C or 2C or 3C or any current that the pack has to be delivered for the designated time. Like for example, if the pack is designed or if the cell is chosen to deliver 5C for 30 seconds, the power cable should also be able to deliver that without overheating or without melting or without leading to fire. So that is something which has to be done. So usually these power cables can be copper or aluminum. They also can be evaluated like using the Ohm's law, which is V is equal to IR. So when we select a wire or the area of the wire, the diameter of the wire, we should be also considering the resistance of the wire so that it has lower resistance. Higher resistance will always lead to increase in the temperature, and also it should be taken care that the length of the wire should be such that there is no significant voltage drop, because being a high voltage system where the dimensions are 1 meter or more than 1.5 meters, you have long wires running around, and that kind of wire should not be leading to voltage drops. So this selection of wire and power cables and all has been a great tradition till now, and there are a lot of information that you could find on internet as well regarding the right wire for the right current rating which you would require. So which is designated as AWG, which is called as American wire gauge. By using this standard, you can choose the right diameter of the wire which it would be able to carrying the right capacity. And also there is a table in the next slide which will give you information on the insulated wires information for different temperatures like 45 degrees, 60 degrees and 90 degrees, which will help you in identifying the right wire for the right power delivery. So here is that we have American wire gauge chart over here where it starts from wire gauge 4/0 or 4 zeros. It goes up to 30 AWG. If you observe over here, you could see that the wire gauge, the first one 000 zeros has a diameter of 11.6 mm, whereas a wire gauge of 30 has 0.28, which means the lower the wire gauge, the diameter of the wire gauge increases, and also if you could see the resistance per unit length, which is leading to the voltage drop. You can calculate it over here. This requires a little bit of understanding on electronic resistivity, electrical resistance, and also the area diameter used. I would leave that small exercise for you to do that. But over here, if you see, the resistance per unit length also increases as your diameter of the wire reduces. That is where you see you need to have a very good area for conducting or transmitting a good amount of current through these wires. So if you have a wire of 4/0, which is at 60 degrees centigrade rating, it can deliver a amp CT of 195. Similarly, if you have it at 75 degrees, it can deliver at amp CT of 230, and at 90 degrees, it can deliver at 260 amp CT. So that means you need to have a wire which is having a suitable insulation material which can resist 90 degrees. It can deliver up to 260 amperes. If you don't have a sufficient insulation material for the wire, then it can fall. You need to choose the right insulation material for your wire so that it can deliver as much as current as possible. If your temperatures are high, if you're operating, that means for example, if you're continuously constantly delivering 2C, 3C current, which means your copper wire is always high, and if you're at 75 degrees temperature and you have insulation of 60 degrees, it will not deliver 230, it will deliver 195 because it will have its own limitations. It will not be able to conduct out heat properly, it will probably melt slowly, and it can catch fire as well. So that is something which you'll have to understand. You need to choose the right insulation material for your wire conductor. And you need to find out what would be the temperature rise in that wire when the current is passed through it, and then only you can deliver 260. But this looks quite impressive. This kind of current where it can handle at 90 degrees centigrade insulation material for the wire is good. Like, you need to choose the right power, right current, right temperature, right insulation material, and right length, so that you don't have much voltage drop. You don't witness any problems over the coming life cycles that the pack has to be delivered throughout. So yes, by this we come to end of this session. So to summarize and all, I firstly believe, I hope you had a good session. You might have understand well all these things. So what we discussed on was like, what are the major differences between lithium ion cell form factors, what are those advantages and disadvantages, and what are the chemistries of lithium ion cells, how these cells are converted to modules and then to packs, what are the differences between the module and pack conversion with respect to cell form factors, what are the important considerations that has to be considered when we select a cell for specific application, what are the different BOM parts, module design, and what significance it plays, and what are the series and parallel combinations in the module, and how do we connect these cells in series and parallel combination, what are those things that needs to be addressed when we connect those modules in pack, etc. And we understood like how cooling plates are to be derived at, etc. So in short, this is how this session would be. I hope this would be very useful to you. These are some of the image credits, thanks to all these OEMs who have helped us so that we could get a better explanation on all the things which we have. Welcome back everyone. This session is week 2 and we will be covering the topic which would be related to lithium ion cell to cell interconnections, thermal load calculations, and IP design. Just to recap on what we did last week. So in the previous week session, where we concentrated on lithium ion cell chemistries, different form factors, the main differences between them, advantages and disadvantages. When it comes to lithium ion cell chemistries, how are the voltages differing for each chemistry, and what are the constructions of the cell, what are the advantages and disadvantages. And we also had topics which are related to cell to module to pack conversion, what are the different form factors, what are all the parts that are needed in a module for cylindrical cell, pouch cell, etc. And we went through a case study based on how a cell has to be selected, different form factors, several factors like C rates, life cycles, SoC percent, and that means the voltage cutoff, dimensions of cells, temperature limits, etc. And how a cell block has to be assembled considering a thermal foam, HCP, etc. And so there was also a session where we understood the cell arrangement has to be happen in a series and parallel combination in a module, and how are they configured in a module, and how are the modules translated into a pack, what are the volume needs for a cell, electronic components and other components. So we also had what are the different components available and what are the role of those components in the whole battery pack, which could be electrical, mechanical, electronics, etc. And we also had a topic which we were discussing on the power cable requirement and the selection of right power cables. So in brief, those were the topics which we had in the last week. And in this week, this is the table of contents where we have sessions mostly focusing on what are the different types of cell interconnections, what is the need of a weld joint, its advantages and disadvantages related to each process of welding, and we have a comparison between those technologies. This session would also be focused on various important topics like battery pack design, which is thermal loop design, thermal interface material considerations, which will also involve, this session will also involve the Ingress Protection classifications, type of sealings needed for the battery pack, etc. Learning objectives. So as explained in our content slide, we would study mostly on the materials used for the busbar, cell to cell interconnections, which material is best and why having a proper material gives us advantages, and how and what are the effects of bad welding, or a poor welding, and what is the performance on the battery pack. We'll also discuss on those principles involved in brief. And then we'll have a good session, amount of session concentrating on the thermal part designs, which include the SoC percent based findings, how the heat is generated at different SoC, a little bit of mathematical expressions using law of conduction, and understand the temperature rise in the cell. What are the certain guidelines that we need to be followed while we design a good ingress protection pack or a gasket design. So we'll look on how to do that, and an overview of different types of sealings that are used in the battery pack. So this would be the objectives of this session, and now quickly let us go into the session where we'll start with the different types of cell interconnections. So in this section, firstly we'll go through different welding methods that could be used in lithium-ion cells and their working principle in brief. So let us start when we say like most widely used welding techniques are for joining one cell to another cell using a busbar. So that is how the cells are interconnected using a busbar, and these welding connections can be done through different technologies. And as lithium-ion cell exists in different form factors, which makes the construction and the casing or the enclosure different materials, a certain welding could not be used for a few of them. So different welding techniques are used for different cells, and one cannot be commonized for everyone. So in this process, let us start with cylindrical cells, which is most widely used. Cylindrical cells, and these cylindrical cells are mostly welded by using a technique of spot welding or a wire bonding, but spot welding is very much common throughout the world, and wire bonding is the one which has been lately come into consideration, but it is a little bit costly, but it is good, it is effective. So, and whereas when we go with the prismatic and pouch cells, these are connected through a common approach, which is laser welding, which is common for both. And then whereas pouch cells only have a unique welding method called as ultrasonic welding, which could be used only for pouch cells. And we have also seen how pouch cells would look like the copper tab which it has, the aluminum tab which it has, and the thickness of those tabs are very less. So that means the same spot welding could also be used for those pouch cells, because the tabs of those end terminals or the positive and negative terminals are very thin. We could also use spot welding, but how to angle of weld and where the probes are, that makes a little bit difficult, but still if the jigs and fixtures are designed well, it could be managed. Whereas with the prismatic cells, apart from the laser welding, we have manual cell to cell interconnections also, which could be done through nut and bolt. So this is used in several EVs, by the way, whereas it eliminates a lot of process cost, eliminating high equipment investments, etc. This also seems simple, as the process is just to tighten a bus bar, place a bus bar, use a bolt or a nut and tighten it. But this type of cell connections has its own disadvantages, as we talked in the last session, this can have high contact resistance, and there could also be high chances of bus bar loosening up due to heavy vibrations and mechanical shocks, etc. And therefore having a good joint between a cell to cell through a bus bar is really important, and therefore it has to be torque tightened. But how much can a torque sustain that vibration is something up to a question of a real-time scenario. So it is something which has to be evaluated again and again, or it will also need a maintenance thing, that after a certain number of months or days, the nuts and bolts have to be tightened again and again. So that is something which has to be followed for certain limitations. So if there are certain limitations in welding, there has to be some answers to that. So these are the different types of cell-to-cell interconnections. Then we'll go to the next topic, which is, this is one of those slides. In the earlier slide we see the spot welding. So we have nickel strips, we have cylindrical cells, and they are welded with each other with a probe, which is for spot welding the cells and the bus bars. And the next one is the wire bonding. So we have a bus bar, and we have cylindrical cells, and we have small wires bonding the bus bar and the cylindrical cell. So these are the two techniques for cylindrical cell. And then we have prismatic cell laser welding. So this is a bus bar, and we have placed the bus bar on the top. So remember, prismatic cell can have laser welding, or it could be done through nut and bolt. But here the best one is always the laser welding. but it comes for a cost. So over here, this is a cell which is having a bus bar, and it is welded to the tab of this bus bar, where the fusion happens by melting of the materials to the heat generated. So over here we see everything, all the cells are connected through bus bar, positive, negative, positive, negative, positive, negative, all connected through bus bar. So this is one of the fusion of how bus bars is. So here one thing what we could see here in the prismatic bus bar, how the cell is welded. There is a bare tab which is the unwelded portion. So the construction of the tab is decided that which kind of cell to cell joining is used. So this starts from the cell construction. So if you want to have a tab, for example, if this tab is designed to have a laser welding connection only. If you want to have a tab with a screw and a nut or a bolt, that has to be mentioned to the cell manufacturer, or you need to pick up a cell which is having that kind of construction. So there are different kinds of constructions that a tab can be made, so that has to be conveyed properly if you are looking for a special cell which is made for you. And in fact, you can also make your tab customized according to your application, so that you can use the same technique of cell to cell interconnection joining. But there are again some disadvantages, as we spoke on regarding the nut and bolt one. Laser welding has certain advantages, that when there is a proper fusion, the current losses are not there because there's a good contact found between them, and the resistance while passing the current is less. So what is the importance of right welding joint? So before we go and understand welding process, bus bar, cell, etc., it's important to understand what is the right welding joint, how it has to be rightly done, and what are the impacts of poor welding joint. So just to understand what is the importance of right welding joint, now we know what a cell is, what a cell to bus bar connection is and all. So the only way to join them is welding. Usually if we go with the mechanical terminology, welding is something when you join two different parts or metals together, and over there the strength is the only thing which plays a major role. Whereas when it comes to lithium ion cell, we have cell to cell interconnection with a bus bar used for welding both the cells together. And when that is done, yes, strength is definitely a major concern. It has to be there, strength has to be good, but there is an additional feature which comes up, which is functionality. This additional functionality is the right word, which is the current also has to pass through it without much of a resistance added to that. So which is the most important part for lithium ion cell to cell bus bar welding. So if that is not taken into picture, I think there will be huge resistance add up because of the poor welding joint, and all the current which is passed is going to be emitted out as heat at the bus bar joints. So this is how it is important to know that along with the strength, the right joint has to be made, which it should be very good enough to conduct all the electricity. It should limit as much as possible hotspots formation on the cell to cell interconnects with the bus bar. So before that we choose the right cell to cell design considerations, we need to also understand what is the type of application that this battery pack is going to, and what is the type of C rate that the battery pack is going to witness, so expected to deliver, or the bus bar is going to witness. Because why application is, we also need to understand what is the environment the battery pack is subjected to, and what is the strength the weld joint is required to handle. If it's going to be earth moving equipment or a tractor or any such applications, there will be huge vibrations constantly adding on the bus bars, and it should be very important to assess those kind of vibrations when we make a right welding joint, so that the time and the area of weld joint which we are going to make is decided depending on those kind of applications which we choose. And then what is the C rate of the bus battery pack? Because bus battery pack or a car battery pack or a high voltage battery pack or any battery pack, the C rates that it would deliver matters the most. If you make a battery pack of a high voltage battery pack which is delivering 1C or 2C current, and you have made a bus bar joint which is only capable of taking up to 0.5C or 0.75C, when you withdraw 1C or 2C current, the bus bar joint is going to be generally heated up. One, you would design a wrong bus bar. Two, the area for the joining of the bus bar would be less, and because of that your bus bar would constantly at a higher temperature, and because of that higher temperature there are high chances that the joint between the two metals would slowly break. So that is the reason you should also consider the C rate for the bus bar when you join. And then the most important, what is the type of material that you are going to use for the bus bar to join. Your material used should have good thermal conductivity, it should have good electrical conductivity, it should be weighing less. There are a lot of factors that would come in when you choose the material bus bar, and also the structural integrity of the module. All these are the factors that would creep in, make the right weld joint. If there is a bad cell-to-cell interconnections, definitely these are the following factors which would happen. Like there would be high resistance near the surface and the bus bar tab. The joints would always be overheated, and you will have to withstand high vibration loads, and that would definitely not happen because your joints are always overheated. That's a weak bond, and your bond can break at any point of time due to high vibrations. So I would recommend you to go through this link which is pasted below, which is from a very good OEM who makes all the welding technology machines, which would give you an understanding of how C rates and how the vibration loads, etc., that the bus bar and the cell bond goes through when it is welded, and what a bad cell design would lead to, how the contact resistance of this bus bar makes a major impact on the battery pack performance, etc. This is a good article which you could go through to the internet at a later point of time. So now let us go to the next topic, which is bus bar welding the cell. So let us understand in this sessions like what is the type of bus bar and cell welding technique and principle behind it and the materials used for the bus bar. So the first one is cylindrical cell to cell interconnections. So you know, cylindrical cell to cell interconnections, the spot welding is the most common one, which is widely used throughout for any of the cell. This commonization of this cylindrical cell has gone to such extent that you can readily get a catalog for cylindrical cells, what kind of bus bar it is used. So all these are commonized mostly. But what is not commonized is the process of welding. So each OEM has its own set of traditional procedures to arrive at the right welding parameters. So over here you see a machine which is a spot welding machine, and you have a jig, you have cells with bus bars, and these are the probes needed for welding the cell with the bus bars. So how is it done is this machine sends a short high current pulse which is passed through the two metals, and that helps in bonding the bus bar and the cells together. So that is how a bond is formed between bus bar and the cells. So this is for a very short period of time, and this spot welding technique happens real fast and real quickly. So that's the reason it has been majorly adopted by most of the people using cylindrical cells. So that is a great advantage which this has. So this process can be automated, this process can be manual also. This is what spot welding technique is, and mostly the bus bars used in the spot welding, that is for the cylindrical cells, is the nickel bus bars, or they could either be copper bus bars plated with nickel. Most of them are this one. So usually copper is coated, copper is used with nickel on them so that there is a good conductivity, so that the heat generated is dissipated as fast as possible. These nickel bus bars are available in straight orientation bus bars or zigzag bus bars. So over here we can see we have straight ladder kind of bus bars. These are called ladder nickel bus bars, and these are called zigzag bus bars because ladder in the sense because of their look, how they look like. These are bus bars used for any positive and negative combinations. So irrespective of the positive side or the negative side of the cell, the bus bar can be placed and straightly welded. The positive and the negative tabs do not have any effect on this bus bar. Both can be welded as equal as possible, and both can have a good strength. But one thing over here, which would be as a battery engineer or a battery pack manufacturer or a battery enthusiastic, which you would like to explore is, this machine has a display unit and it has a parameter values over here. So this is where you need to work out. Like on the day one, you would never get a good joint. You will have to test at different parameters. You need to evaluate different parameters for the bus bar, or like it could be different thing, like at what current you would pass, what is the welding time that you want to do, etc. So there is a good amount of trial and error that you need to do to achieve the right welding parameters for the cell and the bus bar to join together. So what are those? That we will find out in the next slide, which is the spot welding parameters. So some of the spot welding parameters which play a vital role are the maximum welding current, and then you have pressing force, and you have electrode diameter. So these are something which are important. So even though you have all the bus bars, you have all the cells available, you have all the cell holders available and all, it's the whole process of welding will be very important in welding. So you'll have to evolve those technologies over a period of time. You cannot get that right. You'll have to do a lot of iterations while doing that. So when we see, we'll just talk a little bit about the nickel strip. So basically we have a nickel strip which would be of 0.15 mm to 0.3 mm, and we have slots at regular intervals, and then we have a welding electrode which is placed on the tip on either side of the slot, and because it's a nickel ribbon, it has a slot. The current is forced to travel through the cell, which is the shorter distance for the current to travel. And this can provide a solid weld with less energy and less heat. Question can arise, does spot welding without slot work? Yes. But when that is being done, a large percentage of current passes through nickel strip from one welding probe to other. So which means a large percent of current also leads to large current and large heat being generated. So which would also mean that the amount of nickel required to weld would be enough so that a good joint can form. But it will be a lot more hotter than melting a solder material. Like the temperature can go up to 1455 degrees centigrade. So just to avoid that, just to avoid such kind of high temperatures, so why is such high need? So you can always make a slot. You can create a current path by passing the current through the rest of the surrounding materials. It just acts as a heat sink, so it can spread out much faster when you have open areas over there. So this is how they have been doing. The professional pack companies have been doing, and they have been adding slot all over, so that you do not apply large amount of current, which would lead to large heat generation over there, when you can get the same with a small amount of current for a limited period of time with a slot in between. It's not going to affect much. So, and then we have wire bonding technique, so which is also another important technique which is coming into picture in recent days. So this wire bonding technique is something which has been widely adopted by Tesla, as you might have seen. So unlike spot welding, there is no manual process for wire bonding. It is a fully automatic line, and it has several advantages compared to spot welding. Like here, if we see this image, we could see the cell's positive portion, tap portion, is fused with aluminium string to a bus bar. That's the welding mechanism, and the current is passed through these wires bonded on both the sides. So when there are more than two wires for a cell, depending on the diameter of the cell, like for this you can see only one. If the cell is bigger and you want higher currents, or you want much more stability, instead of one wire you could put two wires or three wires, but again the diameter of the cell should be sufficient enough for you to do that. For example, 18650 cell will not be able to support the wire bonding technique because of its smaller diameter. That's the reason the wire bonding starts with 21700 cells, and that's what Tesla has been doing. So some of the advantages of this is like wire bonding. This wire bond is basically aluminium, and aluminium has better thermal and electrical conductivity compared to nickel. Since the wire bonding is aluminium, it can take high currents. And if more high current is passed through these wires, what happens is then the required current. So this wire is designed for a certain specific current, and that is how this wire bonding is done. If the cell is delivering such high current, that means if the cell is misbehaving and the cell delivers any amount of high current, the immediate thing what happens is this wire acts as a fuse. So this being aluminium material, which is having a certain specific melting point for this area, if high current is being transferred through this, because of that high current being transferred, this wire bond immediately acts as a fuse, and it melts and it breaks itself from the other group of cells. By doing this, which means there is one cell which is misbehaving, and that cell is out of the loop, which means the whole module is safe now. You don't have to be worried that one heat from one cell is going to be translated to other cell, and in that way all the cells catch fire. So that is the common case in most of the permanent welding techniques like laser welding or spot welding. But in this one, the fuse itself, the wire itself acts as a fuse, which is a great advantage for this one. At the same time, we have aluminium. When this aluminium is the current carrying path from the cell to the bus bar, it being aluminium, it can always conduct away heat outside through radiation. So the heat is always being dissipated. So the bus bars or the fuse links are never hot when compared to what a spot welding technique would be. So these are certain advantages of having a wire bond. Like what they are, like it is a fully and fast automatic process. Links are tested automatically against strength. So you bond the wire, and the same machine would test it for its strength. So it will have a pull mechanism. It will hold the wire and pull it to see that the bond is good or not. And one more advantage over here is what happens is, if it's a spot welding, if you see here, there is a permanent joint which is formed over here, and if the bond breaks, which means you will have no other option to weld it again. Whereas in this cylindrical cell, if the bond breaks, it's very easy to service this again. You will not have to damage or throw away the whole module. You can again rework on this. You can again put a fuse, you can remove the small particles over here, and you can put another joint and use the module again. So it gives a great leverage in reusing the whole battery pack again. There is no wastage. And then being aluminum material of the wire, it has a better thermal dissipation. And then because this is aluminium and this is reducing a lot of material, which when compared to nickel, the whole weight of the pack comes down. And yes, it also has lower weld resistance when compared to any other spot welding techniques, etc. So these are the advantages of wire bonding, but the only disadvantage could be with respect to our Indian conditions, so where there are a lot of potholes, lot of uneven roads, etc. It little bit makes more complicated for using wire bond design. It has to be designed so that it is intact against the vibrations, and this is a little bit expensive. This equipment comes with a certain cost, but yes, if there are a lot of advantages which overcome this, that could be brought down as well. Now we'll understand what is the difference between wire bonding and spot welding by going through a thermal mapping of this process. Now here we have two different areas, two different columns, where we have one module. The module is the same, it's 7S16P module, but one of the thermal analysis done is with a wire bonding technique, and the other one is with a spot welding technique. So by doing this, what is that we are going to understand over here? So if we see carefully, the one with the wire bonding has same number of cells, the one with the spot welding has same number of cells, but you see a wide temperature difference between both of them. What we could see over here is, for a wire bonding, the average temperature of the whole module is 54.2. The maximum temperature is 56.5, and the gradient, that means the cell of the lowest temperature and the cell with the highest temperature will have a gradient temperature of just 4.5 degrees. So the difference is just 4.5 degrees. But whereas when we see a spot welding with nickel bus bars, the average temperature is 68.6 degrees and highest temperature is 75.9, where the gradient temperature, which is the hottest and the lowest cell temperature, is 14.7 degrees. So you just see the difference between the temperatures of this. So there's a huge difference, which means when we go with a spot welding, some of the cells will always be at higher temperature, whereas some of the cells will always be at lower temperature, which will create a great imbalance between all the cells, because the cells at higher temperature will be deteriorating faster, and whereas the cells at lower temperature will deteriorate slowly, which means the cells will lose its capacity faster and these cells will not lose its capacity faster, and that would create a great imbalance between cell, and the BMS will not be able to handle such kind of differences in terms of voltages, and eventually you will see that the pack will terminate as quickly as possible. So that is how the whole thing gets affected. Whereas when it comes to wire bonding, since we have aluminium bonds everywhere, the amount of heat which is going to be generated by all the cells will always be constant, because aluminium is constantly emitting out heat as much as possible. Instead of being a heat trap, the heats are always liberated as much as possible. So that is one major difference that you'll find for a wire bonding and a spot welding technique. Though the cost of the cells higher, but if you see the performance wise, this is something which you will be impressed with the wire bonding, because the gradient temperature is just 4.5 degrees, whereas the spot welding gradient is 14.7 degrees, which is like 3 times higher, which means the life of the wire bonding would be 3 times more better than that of a life of a spot welding module. So this is the outcome of this one. So it's important to understand both of them and choose the right spot welding or wire bonding technique. So let us now discuss on laser welding, cell to cell interconnections. So laser welding and ultrasonic welding are something which is most common for the pouch cells, and laser welding is a little bit complicated when it comes to other techniques, because laser welding requires a good clamping system where we need to clamp both the bus bar and the cell at the right place, at the right joint, so that the fusion happens correctly, or there could be wrong points where we could fuse it and the joint might not be as perfect as needed. So, and also laser welding allows welding of any material bus bar, like aluminum bus bar can be used, or a copper bus bar can be used, or a nickel bus bar. A nickel coated copper bus bar can be used, and usually copper bus bars are coated with nickel to avoid any oxidation or any such things to happen, because copper tends to oxidize when it is heated or it is fused. So these are certain safety or precautionary steps that are taken while using or choosing a correct bus bar. And now if we see the kind of materials which are used for the bus bar is usually when we have 3 different materials, copper, nickel or aluminium. We always should be choosing a material which is low weight, which has better thermal conductivity and good electrical conductivity. So in that way we could choose aluminium because its density is less when compared to copper, but even though copper has a very good electrical and thermal conductivity, the weight is something which plays a major role over here, and that is the reason we could choose bus bar which is of low weight, which has good electrical and thermal properties. So that is one of the reason where aluminium comes into picture. It plays a very strong role in most of the bus bar materials needed for cell to cell interconnection, especially for laser welding. So now if you see laser welding, we can see here there are 2 different ways to join the positive and the negative of the cell. So here there are 2 ways where we can join cell to cell directly, or we use cell to bus bar to cell. So we have copper tab, which is of very thin size, and usually this is for a pouch cell, and since we are talking about a pouch cell, the tabs are very thin and the bus bar also has to be of same thickness or equal or a little bit more thickness than what it is. So when we talk on the first one, which is cell to cell, you have a probe and you can join it in a straight line. This is the joining area, which means the cell of the first one, I mean the negative or a positive of the first bar, first cell is connected to the next cell's positive or negative through a straight line. This is called the tab to tab joint. So this is the cell to cell is directly joined. You're not going to use any bus bar over here. So that is one advantage that you get with the laser welding for pouch cell, because the weight that is taken by the bus bar is eliminated completely. But whereas there is also another technique where you use a bus bar to the cell, and then this other side of the bus bar is joined to the other side of the cell. So over here also you could see a straight line. So this is one advantage of this bus bar, where you can have a U joint. By doing a U joint, your tabs are always straight, and by bending the tabs you can always form heat affected zones over here, because if the bend is not right, there could be resistance built up over there. So the bending radius of the cell is also something which has to be iterated and it has to be arrived accordingly. But whereas when you have a straight tab, you don't need to bend it. So when your bend is straight, there is no resistance or no heat affected zones forming over a straight object. So that is the advantage which you get over the cell to bus bar and cell to cell combination. So there is a certain trade-off that has to be made in this kind of technique which is used. Whether you use a cell to cell, avoid the bus bar weight, and take care of your bending radius appropriately so that you can get a good joint and the functionality is served, or you take a little bit of lenience, or you can say you are safe. You wanted to play safe by using a bus bar and keep the tab straight, which is a safe game. and then you weld the joint. You join the bus bar to the cell tab, and the other cell tab is joined to this bus bar, and still you can still work with this. So both are equally good. It's just that you need to make a good trade-off which one you want to. So now here we see a prismatic cell laser welding. And as we have seen that laser welding and ultrasonic welding are common for pouch cells. Similarly, laser welding is used for prismatic cells as well. And here we see 3 different cases for prismatic cells, where we have the first one which we would say as a good joint, the second one which we would say as a average, and the third one is a poor joint. So how do we classify it? We classify it depending on the kind of joint by looking with a naked eye initially. So if we see a naked eye, with a naked eye, we can see that the first 2 joints are almost same. We would feel that the first one is a joint where there's a lot of fusion happened, a lot of filler material is used, and the second joint is something where that amount of fusion has not happened, but the joint weld looks good. But the third one is definitely a bad joint even with a naked eye. So if you see the first one, there is a proper contact and a proper fusion formed between the bus bar and the cell tab. That we can see it over here. There is everything is red, which means the filler or the metals have been fused perfectly. When with this kind of joint, what happens is when the current passes, the current has the whole area available for it to pass through the bus bar, from the cell terminal to the bus bar, to the another bus bar, or to the power cable. There's a lot amount of area available, so it can pass through this area and it will pass through the whole bus bar, so that there is no resistance, there is no contact resistance build up over here. So this helps in maintaining low contact resistance and low temperature build up over here. Whereas when you see the next one, you can see the pockets of area which has been left vacant, which means there are certain places where the metal has not fused well. When that happens, when the current is passed through these bus bars, this area of the creamish area which is left blank is something where you have voids, and the current can never pass through this, which makes the current to pass through the same area you'll have to pass more current through the less area, which increase the contact resistance of the whole operation. So you'll have to witness higher temperatures over here. You'll have to witness hot spots at these locations, and this area where it is not welded will act as a void, and it will not allow much current to pass through it. So it's always to be seen that the current has enough area to pass through. This will create a bad joint, and literally after a period of time when there is high amount of current passing through, it will damage the whole joint. So that is what going to happen over here. And then the third one is something which is a very poor joint. Even with the naked eye you can see that there are pockets of welds formed, and when the current has to pass through that, the current will not even pass through this, and there will be very little bit amount of current which will pass through this, and that is going to be liberated out as heat. This is what a good average and a poor joint would look like, and I would always prefer this kind of joint rather than this and this joint. The second joint can be improved a lot, so that the current has maximum area for it to transfer and without generating much amount of heat. So the next concept is ultrasonic welding for pouch cells. This is a unique concept which is only suitable for pouch cells. The reason why this is only suitable for pouch cells is the tabs of the pouch cell, as we saw earlier, they are very thin, and if we want to join one tab or to the other with a bus bar or directly, the metal to metal thickness has to be as less as possible, because there is no heat or any laser being used for this kind of process of welding. So everything over here is micro welding, and it is done through vibration by a clamping force. So the advantage of this is any two dissimilar metals also can be used for this ultrasonic welding. So this is actually a combination of 4 forces together, as mentioned over here. We have micro melting, we have metal interlocking, which is mainly due to plastic deformation, and we have atomic diffusion and metallic bonding. So what happens is you have an anvil which is completely stationary, and you have a workpiece over here, and you have a sonotrode which is giving sufficient clamping force, and it starts vibrating. And with that kind of vibration, there is a metal interlocking formed because of plastic deformation of both the materials, and they get fused together. So this is what we see in the next. There is a weld which is formed over here. So when we translate that to a pouch cell, here is what we can see, a clear picture of what happens over here. We have 3 different cells. We have 3 bus bars which are put together, and then we have 3 tabs of the cells which are in contact with the bus bar, and then we have a support or anvil which is coming over here, and we have a sonotrode which comes in contact with these tabs with the bus bars, and it starts vibrating over here. And with that kind of vibration, there would be ultrasonic, this is by ultrasonic vibrations, and with that there will be metal to metal interlocking which takes place between these tabs and the bus bars, and that's how a joint would form. And one advantage, as we said, the tabs can be aluminium and this can be copper, and though both of them can be joined, but there would be a limitation in terms of thickness of these bus bars and the tabs, and also how the arrangement of this bus bar. If this is something to be done, it is easy because the tabs are facing on the top, like in the vertical direction. But if there is something that to be welded on a horizontal direction, the whole setup would be different, and it would be a little bit difficult if you want to do with a prismatic cell, because usually the bus bar thickness of the prismatic cell and all would be at least 5 mm thick or 4 mm thick and all, and the tabs which are used for pouch cells are hardly 0.25 or 0.3 mm thick. So this makes those kind of welding techniques like ultrasonic welding easy when we have thinner bus bars and thinner tab materials, which is the case for pouch cells. Now the next slide is we will concentrate on the factors for hotspots on the bus bars. Now till now we have seen and gone across different welding techniques, different cell types. What are the bus bars, how are they clamped, how are they welded together. This is the reason why we are concentrating on bus bar and cell to cell interconnections so much, because when we have a group of cells put together, a common thing which we will find out is the hotspot, and that is definitely going to be the bus bar portion. That means when there is an interconnection between the cell to cell, that is the portion where you will always find hotspot. And that hotspots, some of the major factors for that are the bus bar materials resistance, what is the conductivity of that bus bar, and the next one is the weld joint resistance and the current capability of the bus bar, and the cell tab bending, which is the case for pouch cells, and wrong welding parameters. So all these are something which we have discussed in the previous slides. What could a current carrying capability do? For example, what does current carrying capability mean is you have selected a good material, like you have selected an aluminium material, but you have taken a wrong area. You have not considered the right amount of bus bar width and thickness, and you have chosen the best material. That means you are pumping in more amount of current than that material is supposed to carry, and that would lead to a hotspot. That would lead to the bus bar to be hot always. So it's not just the material that plays an important role, it is also the current carrying capability, which is the dimensions of the bus bar, also plays a very important role in avoiding hotspots for the bus bars, and also the resistance of the material, bus bar material, since the popular materials which we have are copper, nickel or aluminium. It also is important to weigh which material has a good thermal conductivity and the lowest electrical resistance, so that the job of carrying the current to the bus bar is done well. So these are some of the factors that we would consider for the bus bar. When we say about cell tab bending allowance, when we saw in the laser welding of cell to tab bending, when we say one cell tab is bent onto the other cell, it is very important to maintain a certain bending radius, typically like 0.2t or 0.25t or so. If that is not done, what happens is the tab which is bent for the pouch cell, there is a continuous stress that would be acting on the electrode which is inside the pouch cell. So if that bending is not done, if it is overbent, the seals of the bus bar or the seals of the pouch cell and all the enclosure material which is used, the aluminium foil externally used, will slowly start rupturing over there. So that is why the cell bending allowance is very important, to do a right joint between cell to cell, joined when it's a pouch cell. So now let us discuss on busbar selection parameters. So till now we have talked about welding techniques, so we have talked about different cell form factors, how are they joined together, etc. Now let us a little bit discuss on the material matrix of the busbar. Now over here we have considered 4 different materials. We have copper, we have aluminum, we have silver, we have nickel, and I have listed out over here electrical resistivity, thermal conductivity and density. So when we say over here, obviously we'll choose the best material, like material which has the lowest thermal resistivity, lowest electrical resistivity, and which has the best thermal conductivity. So if we choose that, if we see the best material, we'll find is silver. Definitely silver is not an option because of its cost, and silver has the lowest electrical resistivity of all 4. It has the best thermal conductivity of all 4, and the cost is high, but you need to also see the density. The density itself is also higher than all the materials. So being it a costliest metal and also the density is something which we can avoid using silver, because it's a highly cost bearing element. So then the next focus shifts on the next better material in terms of electrical resistivity, which is copper. It has the lowest electrical resistivity, like 1.68, and it has a very good thermal conductivity of 3.85, and then it has a density which is much lower than silver, but which is very much higher, like 3 to 4 times higher than that of aluminium. So copper can be an option, but the weight is something which we have to look at. So this would make a same busbar of same dimensions 3 to 4 times more heavier than what an aluminium would do. But if we see aluminium, it has a decent electrical resistivity which is 2.65, and compared to electrical resistivity, it is 1 unit more, 1 digit more than what electrical resistivity is, and thermal conductivity is approximately half of it, and the weight is 3 times less of it. So if we see in either ways, we can have a good trade-off by having aluminium material with a decent electrical resistivity and a good thermal conductivity, and also much lesser in weight. So this is how we could choose a right material. If weight is not a concern, yes, copper can be a great option because it has everything well performing parameters for copper, but aluminium is selected because this is EV. In EV, weight is very crucial. If it's having high weight, the whole pack, whole essence of making a pack itself goes down, because we cannot have a very heavy pack that itself delivering the power would not make a good vehicle at all. So you need to make sure that every component you choose has to be accounted for its weight also. So that's how aluminium can be a good material for busbar selection. Now we'll understand how do we generate, how do we understand the current carrying capability or the dimensions of the busbar. So if we go with the normal law of thermodynamics, this is something which you might have read, like heat is generated I square RT. I is the current carried, R is the material resistance, and T is the time for passing current. So material resistance is something which is dependent on the material resistivity, which is a function of area, which is a function of width, thickness, length, etc. So this is something which I would leave it to you for you to do some exercise on, where you have all the electrical resistivities of the material. You could choose any area or any busbar of any thickness, any length and width, and depending on that you arrive at a material resistance, and then you select a current, maybe 100 amps or 200 amps, and then for how much amount of time you want to pass the current. So your material resistance is dependent on width and thickness and also length, which you want to have from one cell to another cell, which is variable. Depending on that, you will understand what is the heat generated for a busbar. Now that is heat generated for the busbar. Now we would also like to understand what is the heat generated in a cell. So now it is also using the same formula, which is Q is equal to I square RT, where I is the current delivered by the cell, R is the resistance of the cell, which varies at different SoC percent. This is something which we'll discuss in detail in the next slides, where resistance is not at all common for a cell at all times. So unlike busbar, where you can take a constant resistance, that is not the case with lithium-ion cell. Each SoC it will have a different resistance, and then you have time for delivery. time for current delivery. Now the example which I have taken is a cell with 100 Ah which has a resistance of 0.5 milliohms, and we are assuming a resistance for that instance of time for a particular SoC only. It is 0.5 milliohms and it delivers 100 amperes of current for 1 hour, which is at 1C, and the total heat generated would be, we would be using the same equation, Q is equal to I square RT, and by equating that we will be getting 5 watts, and then we give it for Q is equal to mCp delta T, and we have considered the mass of this cell to be 1980 grams, and the specific heat capacity of any material is 1.35, and that you multiply with delta T, and you get a delta T of 6.7 degrees at 1C. So you can see that there is a delta T when you discharge a cell at 100 amps for 1 hour. You can see a delta T of 6.5 degrees. These values are subjected to change, and you can take these values from any of the cell OEMs by understanding what is the weight of their cell and what is the specific energy capacity of their cell. So, and then you could quickly calculate it. But this is just for theoretical calculations, but you want to have a very good picture on how the heat generated is there in the cell at different SoC, because you are going to discharge the cell from 100% to 0%. Your SoC is changing, and so is your internal resistance. So which means your current heat generation also changes with respect to cell, with respect to cell's SoC, with respect to current, and with respect to time of delivery. So this is a dynamic equation which we have to do extensive testing to understand each and every parameter of the cell. So now, as I said, now the resistance of the cell varies with respect to SoC percent. We'll discuss that in detail. So now we'll understand what is the effect of SoC percent on internal resistance. This is not just the effect of SoC on internal resistance. Here we can also understand how, in the same graph, we can also understand how the resistance is built up with different C rates. And here you have assumed the operating window, saying as the best operating window, and we have on x-axis we have SoC percent, and we have internal resistance on the y-axis. So if you carefully observe, when the cell is at 0% SoC and when the cell is at 100% SoC, when it is 0 to 10% and it is 90 to 100%, the cell's resistance are quite high on both the sides. And whereas when you assume it from 10% to 90%, the SoC is almost within the same range. So this is what it shows that why do you have a need to avoid the first 10% and the last 10% of the cell to avoid a usable SoC window. So you basically cut off the higher resistance windows which is responsible for generation of heat more than what it is from 10 to 90%. So by doing that, you are avoiding stresses on the cells. So let us discuss as per the C rate. Now let us see a cell when it is discharged at 0.3 amperes. So when you are discharging a cell at 0.3 amperes, when it's at 0% SoC, and you are trying to discharge a cell, which means, just see, for example, your cell is at 100 Ah, 100% fully charged, and you are discharging, which means it will have a resistance of 0.2. And if your SoC is almost at 0% and you are trying to discharge, your resistance is going to be higher than that. It's going to be 0.205 or near to 0.21. So when your resistance are so high, your amount of heat generation is directly proportional to that resistance. Whereas if you chop off the first 10% and you chop off the last 10% and you operate from 10% to 90%, even though this 10% becomes your 0%, when you start off, you are at 0.19. So when that is the resistance level you are playing at, and at 90% also, you are at 0.195. So you are almost 0.1 less than what, that means 10 times less than what you are starting with. So this is how you understand that why is it so important to resist using the whole SoC window, the whole band of voltage, and use only the best operating window always. So this not only tells you the voltage cutoffs, etc. This also tells you how your resistance varies with different SoC percent. So it's very important to do a very extensive testing to understand what is the internal resistance of the cell at different SoC, and then you map the thermal heat generation of the cell and then translate that into temperature rise. That is how you have to do a thermal load calculation or thermal loop calculation from the cell testing, and then you slowly develop into a thermal loop design model, and then you choose the right material to dissipate the heat or the right cooling mechanism to dissipate the heat. And the same graph over here also shows how at different C rates your resistance builds up. Like for the same SoC window, 10% to 90%, as your C rate is going up, as you are trying to draw more power from the same cell, your resistance values are increasing accordingly. So the resistance at 10% for a 0.3 is something around 0.19 or 0.1925. Whereas when you want to do at 3 amperes, now you could see that it is more than 0.205. So it is much more higher than what it is at 0.3. So this is also one factor which is leading to heat generation. So it is important to understand all these characteristics of how SoC percent is playing an important role in the effect of internal resistance. Also, how you need to avoid the first 10 and last 10% of the voltage windows, so that you don't enter into that highly stressed zone. And also you have operating temperature also, because when you have higher operating temperature, as I said, like the electrolyte which is there inside slowly gets vaporized, and once that is done, the ion movement becomes difficult. So that is also one of the reason where the internal resistance builds up because of higher operating temperature. And what is the effect of internal resistance? As we see in the previous equation, internal resistance R is directly proportional to heat generated, and current is also inversely proportional to heat generated. The more you draw current, your heat generated is increasing, and the more resistance is increasing, your heat generated is also increasing. You need to see where is your best operating window, and with that, how much is the heat being generated, and with that, how do you choose the right cooling material or a cooling design for that. Now let us enter into the thermal dissipation loop and thermal interface material considerations needed for a cell. In this topic, we'll understand how to extract the heat from the cell, like through various mediums. Till now, we have been talking on what are the causes of heat generation, how do we understand the resistance, SoC, and how do we mitigate that and lower the heat generation. Now we'll be concentrating on how to dissipate the heat and how do we design that. So here we'll understand some of the thermal materials which are used in cell or a pack or an enclosure, etc. So if we see over here, there is a small schematic which we have earlier we have seen a cell, thermal material and a pad. Similar is the condition if we want to use for a cell. So this is the thermal pad or a thermal interface material. So what does it do? Because when we are going to have a cell to cell or a cell to heat sink contact, there are a lot of air gaps that would be formed which acts as insulators. So that is something which has to be avoided as much as possible, so that there is a seamless thermal conducting medium from the cell to the heat sink or an enclosure or any other source which dissipates the heat. So this is what happens. The cell generates heat. It is passed to the enclosure, which could be aluminium, through a thermal interface material. And that thermal interface material is something not new. It has been in existence from many years. And it is available in different forms. It is available in thermal pads, it is available in thermal foams or thermal paste. But what is the science behind it is the selection of the right material and thermal conductivity is something which is very important, and that is something which we'll have to do it over a period of time by understanding the cell heat generation and the temperature reached. So when we talk about the schematic diagram again, we can see that there is a cell and we have a thermal pad in between an enclosure. And enclosure, when I said it has to be aluminium, because aluminium has good thermal conductivity. Whereas if we are using a thermal pad and a cell and we are using a MS enclosure, and that MS enclosure is usually powder coated, and MS enclosure, mild steel, is a very bad conductor of heat. It doesn't conduct anything at all. So it doesn't even make sense if we use and we have a cell and then we are using MS enclosure. It's waste of effort. So a proper right combination has to be made always when we are putting different materials together. So if we are using a thermal pad, it has to be made sure that the enclosure being used also has a very good conductivity, or the essence of using a thermal pad is completely lost. So that is something one of the important consideration when it comes to thermal dissipation considerations. So the next slide is thermal interface material conditions, where I would just like to say that TIM is thermal interface materials and I would be calling it as TIM just to cut short. The thermal conductivity of TIM is something which is very important. So the TIM is being in use from many applications, like it is being used in power electronics like MOSFETs mainly to dissipate heat because they generate a lot of heat. So hence the application, their use remains the same, but the thermal look and its design and its application differ. So some of the considerations needed are like the thermal conductivity of the material should be as high as 5 watt per meter Kelvin, but that comes for a price. So it is important to have a good trade-off between the cost, its application and the performance also. So it has to be selected properly, and we need to understand the maximum temperature rise that happens in the cell, and then we select the thermal conductivity of the material equally. It doesn't make sense like we choose a very high thermal conductivity material when the heat generation is very low. So it is that, like, it is very important is the area of application. So just to give some heads up, like it is recommended to go through week 1 session where you could understand where we have all the thermal pads written. Like you could refer the module design for the pouch cell, module design for the prismatic cell, where we see a lot of thermal interface materials placed on metal plates placed over there. So over here, just to refer that, some of the area of applications of thermal interface materials are within a battery module. We have a cell and a heat carrier plate which is applicable for pouch cell, and then we can have the same thermal interface material between cell and then external enclosure. And then we have types of form factors, so different cell form factors and application. So it differs from the types of form factor and application. For example, if it's a cylindrical cell, you cannot use it across the body, but you could across any one side of this one. So but application is like where are you going to use it and how much of the heat is going to be generated there. And then also you need to consider the set of compression forces that are required for assembly. For example, if you are going to use a thermal interface material of foam and you are going to use it for pouch cells, you need to understand what is the compression force required to compress it so that it is of actual right use to you to avoid expansion and contraction of the cells. Then the most important part is, are you going to use a thermal interface pad or a foam, so that when you have set of cells over here and you are going to slide all these cells into the module, how easy the assembly is going to be. And that is something which is to be evaluated. So whether you're going to use pad or a foam or a paste, and how easy the assembling sequence is going to be. That is something which you have to look at. So there are multiple considerations for a thermal interface materials to be selected on. It doesn't happen over a period of time. You need to evaluate a lot of conditions for that and then arrive at the right thermal interface material. And then what is the thermal design loop for a pouch cell? So I would suggest you to refer the week 1 session again, just to have an idea on the thermal interface on the module design concept over here. Or the process of thermal design loop for the pouch cell is like this. This has the pouch cell come in different form factors, and each cell has a different form factor. When I say form factor, it is in the terms of dimension, and the enclosure design is completely different. So therefore the thermal loop sequence has to follow in this way, that when there is a compression foam, it has to accommodate the expansion and contraction of the cells. So that means you have a cell which is 1 mm thick, and you would compress it only up to 70%. That means it becomes 0.7 mm, and you put that between the foam. You put that foam between the cell and the HCP, so that when your cell is expanding, that 0.7% is reduced to 0.2 or 0.3 or 0.4, and whenever the cell is contracting, that 0.7 mm increases to 0.8, 0.9 or 1 mm. So you don't have any space left vacant whenever there is an expansion or contraction going on during charging and discharging. That is something which is very important for a thermal loop design of a pouch cell in selecting the right foam. And then this conducting foam should be having good conductivity. It should have a good electrical resistivity because there is a HCP which is a metal and it is in contact with that. So you should have a good electrical resistivity and also good conductivity. And the next point is the same. HCP, as it is in contact with the cell, the enclosure, or is in contact with the HCP, through there you put a tin there so that the cell is in contact with the HCP through a thermal foam which conducts all the heat to the HCP, and HCP is conducting all the heat to the enclosure through a TIM. That could be either a foam or a paste or a pad. So that is how you design a thermal loop for a pouch cell. So though it was complicated because it's a pouch cell, the thickness is not favorable for us. As I said, pouch cell designs are always complicated, but that is the only way we have to extract as much as heat as possible. This is a pictorial representation of how we can have it. So over here, this is a plate, HCP, and then we have a tube over here, we have a pouch cell. This is a liquid cooled plate. So just to make this whole heat extraction even more effective, we can use a liquid cooling for each cell. So these are the inlet and outlet pipes. Over here is the place where you can put a thermal pad. So that is what we can see over here. So you have a pouch cell and you have a compression foam over here, and you put a HCP on the top of it, and you have several blocks out of that, whereas this HCP or this cell blocks are in contact with the thermal pad with the enclosure. And remember, this enclosure should be a material which is conducting away heat, not a material which is very bad conductor of heat. So you have cell blocks which are in contact with the enclosure through a thermal pad, and you have a pouch cell which is in contact with the HCP using a thermal foam. So your loop is completed. So that is how you need to design everywhere, that you transfer as much as heat from the cell to the enclosure, so that at the enclosure level you either have air going through and the heat is taken away from there. So this is for passive. Whereas if it is active, you can see over here, like you have inlet and outlet collector tubes, and you have water directly running through these channels, and the heat can be extracted away like that. And since these are pouch cells, you can use thermal pads over here, and that gives no air gaps between the cell and the heat carrier plate, and in that way the dissipation is much more better. So the next one is the thermal loop design for prismatic cell. Here we would be at a relief because now we see the prismatic cells, as we discussed earlier. The prismatic cells have certain thickness which makes the whole concept of thermal dissipation very easy. Since we have wider thicknesses, wider areas, everywhere we could put thermal pads directly, and we don't need a complex thermal loop there. Like unlike in a pouch cell, we have a pouch cell, we have a foam, we have a heat carrier plate, and then we have a thermal pad, and then we have an enclosure. Oh, this is really tedious and very complex operation. Whereas in prismatic cell, it becomes very easy. You have surfaces directly over here. You can put thermal pad over here and fix an enclosure on top of that and extract heat. It is as simple as that. So this is the main reason why prismatic cells with higher capacity are always used. It also makes the whole design loop very easy when compared to pouch. So here is a little bit more information on thermal loop design for prismatic cells. So this is a prismatic cell typically used. Let us understand, like the base enclosure, we have aluminum and we have two prismatic cells. And if we see over here, we have very wide thickness for the prismatic cells on both the sides. Like we have area at the bottom. So if seen properly, we have a lot of advantage by using thermal pads on all the three sides, and see that we can extract heat from the side and the bottom as well. So this is one major advantage that we'll have with the prismatic cell compared to pouch cell, that the design loop becomes very easy. There is no much contacts needed, no essential need of one-to-one proper contact always, because as many contacts come into picture, we also have the same resistance add up. There will be a lot of air gaps which will form. The whole process becomes complicated. But over here, we just have a cell. We can put a thermal pad on the side. We can put a thermal pad at the bottom, and we have thermal heat sinks or good thermal conductive heat sinks on the side and the bottom, and the heat generated by the prismatic module is taken away as easy as. So this is one advantage of using prismatic cells like this, unlike pouch cells, which has huge complexity when it's compared with pouch cells. Also, we have direct cell contacts over here, so we don't need to use any HCP over here. We can have a direct contact with the cell. So that is the greatest advantage over here. And now since we have discussed on all these topics of thermal dissipation, thermal loop designs, etc., let us get into a little bit of ingress protection type and what its needs. So ingress protection is something which is dealt with entrant of water or any entrant of dust particles into the battery pack, and that can cause a huge damage to the whole battery pack because there are a lot of electronics sitting inside it. There are a lot of metal objects inside it. The busbar mainly are all conducting materials, and we have cells which are highly conducting material. And if there is any small particle or any metal piece which goes and sits on any of the busbar in contact with any of the other busbar, it's going to lead to short circuit, etc. So that's the main reason why we need to have a very good ingress protection. It's not just that, like if you keep allowing the dust to be accumulated on the busbars, now we have put a serious effort on understanding how important is it for the busbar to have thermal conductivity so that the heat generated through it is always dissipated. Now imagine if that is accumulated by the dust, it's not going to be as effective as it. So those are some things which is really driving the need for ingress protection, and let us go through it, what it says in the next slide. So what is the need for ingress protection? So the most important part for ingress protection is, now the whole IP has been classified into different levels. The whole IP is called ingress protection, and it plays a very important role in the battery pack performance. Like what happens if we have a very bad ingress design? It will allow entry of solid and liquid particles into the battery pack, and when water enters into the battery pack, it can cause a lot of havoc. Like the metal components which are there, like the bus bars or the screws which are used for mounting the cells or the bus bars or the BMS or for tightening the enclosure, etc., everything gets rusted. And if such thing happens, then the whole resistance of the whole pack goes up. It would lead to a bad performance of the whole battery pack. So ingress protection is something which has to be designed properly, and it has to be taken care very seriously. So water ingress is something which can lead to rusting of the battery pack, and the bus bars in contact with that also gets affected because of that, and it can also cause electrical failures. It can cause short circuit because water being one of the major culprit in terms of all short circuits, etc. And there could be a lot of wires with current running through them, and water coming in contact with that can create a havoc. Same is the case with solid ingress protection. So when we have a break in the ingress protection, solid ingress can be anything. It could be dust, it could be metals, it could be solid particles. And when such thing happens, as I told earlier, like dust is accumulated on the bus bar, and when that happens, the bus bar's major design tendency of liberating or dissipating heat as much as possible when the current is passed is lost, because the dust is formed on the cells, and that actually covers the whole bus bar, and it doesn't allow the heat to escape, and it becomes heat trapped there, which eventually leads to overheating of the bus bar over a period of time. And because of that, the whole efficiency of the battery pack goes down because of that. So that is the reason why we need to have a very good ingress protection need. So let us start into the first level of IP protection level, which is IP dash or -X. So when I say solid ingress is mostly related to the first digit of the IP protection level. Usually IPXX is the term which is used, where the first digit is for the solid protection, and the second digit is for the fluid or the liquid protection. So the first one, when I say IP1X, which is the basic one, and IP6X being the highest one. With IP1X, it is to be that there has to be a protection against any solid object which is having anything dia more than 50 mm, like hand. And then if it is IP2X, it should have a protection against those solid objects which is having anything of size greater than 12.5 mm, which is a finger. When it is IP3X, the protection has to be against any object which is having a dia more than 2.5 mm, which could be a screwdriver or any nail or any sharp object, etc. And then IP4X is something where you need to have a protection against a solid object with more than 1 mm dia, which could be wire or any other thing which is like 1 mm. And then IP5X is something against dust protection or limited ingress. So there will be no interference with any of the operating equipment. So this is something which is a little bit higher than 4X. So it is only limited to dust protection. And IP6X is seal tight. So you would not have any particle or any dust particle or anything entering into the battery pack if it is IP6X. So usually the best recommended is IP6 for a solid ingress protection. And similarly, we would see what does it take for a liquid ingress protection levels. So liquid ingress protection levels are again, so as I said earlier, it is IP-X, and in this one, IP-X- is the next. So the next level of protection, which is liquid ingress protection, that is IP-X- or X-. So the second digit is something which is related to the liquid ingress protections. So here, this is something which we will deal against protection against liquids. The first one is something which we will deal with the protection against solid objects. So when we go with IP-X1, we'll have to see that there is a protection against vertical falling drops at a rate of 1 mm per minute for 10 minutes. And then if it is X2, we'll have a little bit more complicated situation we're creating, where we'll have to have a protection against diagonally falling drops up to 15 degrees, and that is also for a rate of 3 mm per minute for 10 minutes. Then IP-X3 is a little bit more higher. So this is the intention, like when we go on increasing like level IP-X1, X2, X3 or IP-1, X2, X3X, the intensity of protection against ingress increases. So the higher the level we are, the better the protection we have against ingress. Similarly is the case with IP-X3, where we are going to spray a water for 5 minutes at 0.7 liters per minute at a pressure of 80 to 100 kilopascal. And then we have IP-X4, where we will be splashing water in all the directions for 5 minutes at a speed of 10 liters per minute for the same pressure, 80 to 100 kilopascal. So here is the directions or images which we can see. First we start with small drops on flat, then we go with inclination, then we have water spray coming in, and second IP-X4 is for all directions, and then IP-X5 over here. Here the whole flow rate, etc., everything gets increased now. Now we are going with a water nozzle instead of a spray for 3 minutes for 12.5. Earlier it was just 10 liters per minute. Now we have increased to 12.5 liters per minute, where the pressure is 30 kilopascal, right, from a distance of 3 meters. And then IP-X6 is even more higher. Like we are going to have a protection against 12.5 meters water nozzle for 3 minutes when the flow rate is 100 liters per minute at 30 kilopascal for the distance of 3 meters. And IP-X7 is it's not even more complicated. From here again, we come into a functional point of view. So when it is IP-X5 or X6, we are looking at it at an angle when someone is throwing water onto the body or battery pack. So here we are going to pressurize water onto the battery pack. But when it comes to X7, the functionality changes. Here we are trying to submerge the battery pack into the water and see whether water is entering into it. So here is another type of design sealing that has to be done. So both are different in their own ways. Over here, when it comes to X5 and X6, people tend to say, oh, it is X7, it is much more good than what it is X5. No, that is not the case. The functionality of this seal ingress design is different. And same is the case for X8. Here we are looking for the ingress against water depths up to 3 meters. So we are going to put the battery pack for longer period, and the depth of that immersion would be more than 3 meters. So that is for IP-X8. Now if you see, there is a slide on where we'll understand what are the different types of serviceable battery packs in the sealing. So usually sealings are to be classified into permanent sealings and serviceable sealings. So when we say about different types of sealing, we have different types of process involved for sealing, which could be a silicon die cut gaskets, which we can see over here. which is a seamless die cut. We use a gasket, and we can have a die of the required shape, and we can die cut it. Then we have foam in place gaskets, which is this. So there is a material, liquidified silicon, which has been melted, and it is injected through this robo arm, and it can take any profile which is needed. It is guided through a robot. We need to program the profile of that, and it is injected through the profile wherever it is needed. But it's just that it takes some time for solidification. But this is something the latest being used in most of the applications, foam in place gaskets. And then we have O-rings, which are the most common ones. So where do we use the serviceable battery pack sealings? Are somewhere where these components are more prone to opening, and again it has to be reworked and again closed back. It is not something which has to be permanently sealed. So battery pack has a lot of places where components can fail and they have to be replaced quite often. Like there could be a BMS burnt up, or some fuse is broken, or some wire is broken. So that means there are a lot of places where the battery pack has to be opened, has to be repaired, and it has to be again put back together. So that is the place where serviceable gaskets are being used, which is like battery pack over here. So that is the place where we need to use serviceable gasket, which is over here. Similarly, since there are a lot of electronic components being in place for a battery pack, like we have BMS, we have fuses, we have telematic boards, etc., there will be a lot of EMI and EMC radiations interferences happening. So that means we need to also have certain gaskets which are already available with some metallic composition with the silicon materials, so that all these radiations and interferences are stopped by these gaskets. So we can also see that we use certain gaskets with EMI and EMC shielding capabilities, so that the frequencies and there are no noise disturbances that would occur when such radiations are passed through. The BMS is not getting affected, or the telematics are not getting affected, because there are a lot of errors that this EMI and EMC can cause in a battery pack. So that also becomes a most important aspect when we choose the right gasket design. If there are such problems, if we are identifying it, it is important to choose those gaskets which can solve EMI, EMC problems also. Some of the most important design considerations for gasket are this: gasket design must be in such a way that it should not allow ingress at all for any of the objects, be it solid or liquid. So when that happens, the whole essence of using a gasket or a sealing goes. For example, let us consider this holes of this plate which are there, and we have a gasket which is the red portion over here. So when we have a hole on all the four corners, it has to be made sure that the gasket area is inside, not outside. So if these holes are inside the gasket area, which means when the water is in contact with this hole, there are many chances that the water could enter through this hole. So what is the use of having a gasket? There is no need of having a gasket at all when you have a hole inside the gasket. So the whole essence of using it is lost. Whereas if you have the holes outside the gasket area, it makes sure that even if water is coming in contact, your gasket is designed in such a way that all the electronics and other components are lying inside this area, so that even the water comes, it can come and touch your gasket and it is not entering inside it. So this is how you design you take care in designing some of your gasket design. And one of the most important part is the offset between the gasket and the gasket cover. So you need to maintain proper offset between the gasket and its cover, so that when you apply proper torque and when you tighten the gasket enough, the gasket doesn't ooze out when you are applying more pressure to it. And it has to be seen that your gasket is well within the boundaries of the outer cover, and that is something which you have to take care of. And also the gasket has to be tightened. This cover with the other cover has to be tightened by using screws and nuts and bolts, etc. And when they're doing that, you need to see that a proper torque value is applied, or else if you over tighten the whole enclosure with the cover, there are high chances that you might tear open the gasket and it could lead to ingress leakage inside the cover. So this gasket design considerations are a combination of torque, are a combination of placement of the gaskets. It's a combination of how much force you apply and how much you compress the gasket, how do you place the gasket to avoid ingress protection. So it's a combination of all, and how do you assemble becomes even more challenging. You could have a great gasket, you could have a great material, but if you don't assemble it in the right way, you would always lose the gasket's importance over there. And the last important point is the gasket must be seamless, and the joint, the screw and the nut which is used for assembling two plates together, which is responsible for having a sealing, should be strong enough that they don't move away due to vibrations and other shocks, so that the ingress is still intact. So these are some of the design considerations that are needed for a gasket design. So now we'll talk about permanent sealings in a battery pack. So what are the permanent sealings? Like some of the permanent sealings which we always know are welding, riveting, or any other technique, or spot welding, or different types of joints are there which are permanently sealed. But certain permanent sealings cannot be used in battery pack, and certain permanent sealings can always be used in battery pack. So what are those? One of the most important application in a battery pack is the cold plate. So this cold plate houses of cooling tubes, it houses of running water channels through them, and its main importance is it has to hold also the modules together. So this makes it very neat that the cooling tubes, for example, there are copper tubes over here and they are assembled into it, and it has to be a permanent joint. It cannot be a disassembled joint, or if it's a disassembly, or if this joint can be serviceable, which would mean that there could be all these pipes coming out often because of vibrations and all. So to arrest that, it has to be a permanent joint. So there are certain applications in battery pack like cold plates which has to be a permanent sealing, and this has to be leak proof, or else if they are not joined properly, if gaskets or such type of sealings are used, there are high chances that the water, the coolant fluid which is flowing through these cooling plates can come out because of one vibration or one high load jerk. It could open up the whole sealing, and that could damage the whole cells, modules which are inside it. It could cause a catastrophic effect on the whole battery pack. So that is the main reason why we need to have a permanent sealing for these cold plates, so that we have one inlet, one outlet. Just there are two hoses for the inlets and outlets, and those are also sealed. It's just that the water entry pipes, hoses are fixed to that. So everything in a cooling plate is joined. It has to be seamlessly joined, and it also has to be tested against ingress. It has to be tested against air leaks or water leaks as to the best extent as possible, so that there is no leak when it is assembled on the battery pack. And it's not just a cooling plate. It also must be able to withstand the vibrations. It must be able to take the load of the modules on, because they lie on this cooling plate, and cooling plate acts as a base and the important structural member to hold all these modules in the high voltage battery pack. So this is where we use a permanent sealing. So yes, in short, we have come to the last summary slide, where we will, I hope this would be very useful to you, where we have discussed a lot on thermal behavior of the cell, what is the internal heat generation, what are the different welding techniques used, what are different welding principles we have, what are the thermal loop designs for cell, a module, and how do we calculate the internal heat generation in a cell and a bus bar, what are the types of materials that we could evaluate for the welding of bus bar, and how do we choose the right form factor and the dimension of the bus bar so that the heat generation in the bus bar is as low as possible. We have also discussed on the internal resistance and its effect, how it's affected with respect to SoC. We have discussed on the different types of ingress protections, which is solid particulate and also the liquid particulate matter. And then we have discussed on the different types of gaskets, what are the different types of sealings that are used in the bus bar and how each sealing has its own importance. So in short, this is the summary of what we have done in this session. I hope this has been a useful session for you, and I would like to thank everyone in the image credits with whose help we were able to understand the phenomena and the science behind each and everything in a better way. Hello and welcome back, everyone. This is the third week of lithium-ion battery pack design considerations, And in this week, we will be mostly concentrating on the most important part, which is the BMS considerations. So in the last couple of weeks, you might have heard about BMS slightly, where we say that the wiring voltage sensors goes to the BMS, and BMS is something where we can program it, etc. So now is such the place where we will be concentrating more on BMS, and we'll understand what are the capabilities of BMS, what are its different architectures, and how does BMS save the battery pack from effect of abusive C rates. What are the main functionalities of BMS? So this is what we would be covering in this week. Start off, we'll have a quick recap on what we did in the previous week. We had a few topics which are related to the types of welding process, what are the busbar materials used, how the welding process is done, what are the different process changes with respect to different form factors of the cells, how is the heat generated in a bus bar, and how is the heat generated in a cell. We also have looked into thermal loop designs for cylindrical cell, pouch cell, prismatic cell. What are the different thermal calculations that is to be done to understand the temperature rise due to the heat generation, which is a combination of internal resistance, SoC, etc. And we also had a session on ingress protection levels, what are the different sealing types and how the gaskets are designed, and what are the different gasket materials used for the battery. So this is a recap of what we did in the week 2, and now what we'll have in the week 3 is this. We would cover the topics related to BMS, what are these terminologies, what are the voltage cutoffs through BMS, what is its effect on the capacity, and what are the different C rates, BMS protection features like C rate protection features, temperature protection features, and we'll also discuss on what is SEI layer. This is something which you might have read somewhere, but we would discuss on this SEI layer, which is the cause of capacity degradation or the failure of a cell, and what is its effect on that. What are the different types of BMSs, and how are they classified into high voltage and low voltage applications. And then we'll also check on what are the low voltage pack architectures along with high voltage architectures. Also we would discuss what are the low voltage architectures, what are its functionalities mainly for high voltage and low voltage, what are the main differences between them, and then we'll touch base again on the cooling plate attributes, how are they integrated and what are the driving factors for the cooling plate, and then we'll also see what are the abusive usage conditions, its effect on the cell, and how does BMS overall at the end you will have understanding how will BMS protect all those abusive usage conditions on the cell. So these are the table of contents, and let us focus on what are the learning objectives. As we saw in the table of contents last week, like our focus week 2 was mostly on the cell and its characteristics and the selection of right cell, how the modules are made in the last 2 weeks, or what are different types of chemistries, form factors, etc. But this session would mainly concentrate on the BMS, which is the heart or brain of the battery pack, which is also mentioned as battery management system. Battery management system, how does it functions? And we'll have understanding on what are the different types of BMS used, what are its objectives, how battery behaves when subjected to different abusive conditions, and how would BMS control it in preventing thermal runaway or failure of the battery pack, etc. So we would also get some idea of understanding the selection of the right BMS for this application, how is the BMS mounted, which area is mounted for the BMS, how does the cell deteriorate due to abusive user behavior, and how does the BMS help in controlling it. So these are some of the objectives of this session which we will go through. So before we go directly into the BMS, we'll understand what is the BMS, voltage terminologies associated with it, so that this would be helpful for you to have a clear and easy understanding in the next coming slides when we talk about BMS. So firstly, what is state of charge? So SoC, we have heard about this in the last 2 weeks number of times. We have heard about DOD number of times. But what does that mean, SoC? We know state of charge, that's the abbreviation of it. But what does SoC mean? So SoC is nothing but the amount of charge that is available in a cell. It is similar to a fuel indicator. Now SoC indicators are also available for the battery pack. You can have a battery pack and you can have a SoC indicator, and that will show the amount of charge that is there in the battery pack. It is similar to a fuel gauge that you have in a normal IC engine. When the fuel is 100%, the tank is full and your indicator shows lowest point, that means your fuel is empty. It is the same over here. SoC indication starts from 0 to 100, where 0 is empty, 100% is full, and this is applicable for charging. That means the amount of charge is left in the battery is what indicated as state of charge. But whereas depth of discharge is the reverse of SoC, which means that is mainly during discharging. So this is a little bit tricky to understand. Like now see, now SoC is the amount of charge. If we have consumed 20% of the energy, which means the SoC is 80% left and 20% is a consumption. But when you say depth of discharge, that means that 20% becomes your depth of discharge. I understand. Like the amount of energy that has been consumed is your depth of discharge. That's the reason we say that is inverse of SoC. So when you say your depth of discharge is 100%, that means you have consumed the whole of the power. You have consumed everything what is there in that. So that is how you say as depth of discharge. So it is the opposite of what SoC is. The amount of energy that has been consumed is called depth of discharge because it has been consumed. So now in this slide, when we talk about depth of discharge in SoC, this will give you a much more clear picture. Also we have cutoff voltages. So maximum voltage of a cell is actually the cell which is actually the voltage that is reached during charging. And we have minimum voltage, that is the voltage which the cell has reached after being discharged. So that are the cutoff voltages which we have already understood. Like we have 3 different voltages, nominal, maximum and minimum, it's the same. Now when we say about SoC, DOD and etc., here is what we need to understand. Now consider this as a cell. The first one being fully charged, SoC up to 100%. The next one, the least one is SoC 0%. So SoC is 100, the inverse is DOD, 0%. And SoC is 0, the inverse is DOD, 100%. So when this amount of energy, this white area is the amount of energy which has been utilized, that becomes the depth of discharge. So this is the amount of depth the discharge has gone up, and the remaining becomes the state of charge. So this amount of charge is still available in the battery, whereas this amount of discharge has taken place. So that becomes the depth of discharge. So usable capacity is nothing but depth of discharge into normal capacity. Now you would understand the equation of what is depth of discharge. It's just the inverse. How much the energy or the discharge you have done, that becomes your depth of discharge. It is as simple as that. Now the next one is the rated capacity versus usable capacity. Till now we have seen that you have a voltage window and you cut off the voltage, your capacity has been dropped, etc., etc. Why do we need to cut the voltage windows? We can use the whole amount of voltage window. These are some questions by now you might have understood. You might have been cleared in an aspect, but you might not also been clear in some aspect. But this slide would help you in understanding. So the whole capacities of a cell can be treated in 2 ways: rated capacity and usable capacity. Rated capacity is a capacity which the cell is designated of. So for example, there is a cell of 100 Ah. That becomes the rated capacity. But that is some capacity which the manufacturer has manufactured it for. So the cell will be able to give 100 Ah when it is operated at its full voltage. But usable capacity is something which is controlled by the OEM who makes a battery pack, or it is controlled by the BMS or an engineer who is working on that cell, saying that I am going to limit the voltage windows, and because of that the capacity is going to fall, but still I am fine with it, which means the usable capacity is going to be less than that of a rated capacity. That is mainly because of the voltage cutoffs which we are going to do. So that is a reason why we have a usable capacity lesser than rated capacity. Now how and why is that happening? Now here we have a small image of that where we have lower line and upper line, which is the battery capacity, and when we fully charge it, there are certain stresses. When we are fully charged, there are going to be charge stresses, and then when we fully discharge it, we are going to have discharge stresses over here. So when we fully charge it, if we limit it to this percent, 80% of charge, and we limit it to 80% of discharge, we are going to avoid the charge and the discharge stress, and we will always be in the low stress zone. So this is the reason why most of the OEM manufacturers avoid touching the higher and the lowest limits always, and because of that the result is we would be losing the capacity. But that's fine when we are not allowing the cell to see the charge and the discharge stresses, which means the cell is operating at a comfort zone, which means we are going to have higher life cycles. So which means we'll need to slightly choose a cell which is having higher capacity, and then we are still fine with it. We will be having all the life cycles that we need. We will be achieving all the life cycles that we need to. So this is how we need to trade off between a rated capacity and the usable capacity. And how is it done? And it is done by programming the BMS by controlling the voltage cutoff. So next slide is like the BMS need and its functionality. So what is the BMS? BMS is called the battery management system, and it is the most important or the main control authority of the battery pack, which is responsible for safe monitoring and the safe functioning of the battery pack. So the major functionalities of this battery pack are like cell monitoring or cell balancing, which is one of the major tasks of BMS, where it monitors to keep all the cell voltages uniform through our operation of the battery pack while charging. So then we discussed on voltage cutoff limits during charging and discharging. Also, we have other safety features for the battery pack, which are temperature protection. That is, it will not allow the battery pack to operate above certain temperature limits. So and how is it done? This is all done through the BMS. This is all done through programming the BMS with the right values which are needed to give all these protections. And then BMS, that being sole communication authority with the BMS, and with the VCU, and it transfers all the parameters like SoC, SOH, all the error indications, or it could also transfer the data like battery pack temperature, operating temperature, whether it is safe or not, etc. So BMS communicates everything with the VCU, and then the VCU takes the appropriate decision what to do and what not to do. And then just not that, BMS also has certain protection features, like BMS also protects overcurrent C rates, like which means when the cell is delivering certain high C rates other than required, then that means the cell is misbehaving, and that kind of C rates are monitored. The BMS cuts off there itself. And also if the vehicle is demanding more power, which the battery pack is not designed, or which the electrical architecture is not designed for, the BMS immediately says this is not within my limit and I would not be able to deliver such kind of currents, and it terminates that command immediately. Such kind of precautions or protections is done by the BMS, which will also safeguard all the electronic components, electrical wiring harness in the battery pack, along with the cells, the incoming current and also the outgoing current. So this is all monitored by the BMS, which means the BMS becomes the vital component of the whole battery pack, which has to be programmed correctly, so that all these precautions and safety are considered while the BMS functionality. So now one of the major functionality of the BMS, that is cell balancing. So let us discuss about cell balancing. So why do we need a cell balancing? Like, we have heard about cell balancing a lot, but why do we need something like this? Because there are n number of lithium ion cells in a module or in a battery pack. And in a battery pack, each cell can behave in its own way. Very difficult to bring all identical cells together, and even if we bring that, even though the behavior of each cell is going to be difficult, and hence when the cells are put to charge, what happens is one of the cell in the module can be charged quickly, whereas the cell which is right next to it, it will be charged slowly. That is what we see in the image over here. So one cell has reached its normal operating voltage range, another cell has reached more, another cell has reached little above, one cell is still less. So with such kind of voltage differences, when we put the cell for charging, if this happens, what happens is, until the other cells are being charged, the cell which has already been charged gets charged even more. It gets a current more and more and more and more, and which will allow that cell to deteriorate faster than the other slow cell which is getting still charged. It's not the fault of the cell which is charged fully. It's not even the fault of cell which is slowly charging. It is just that the cell which is overcharged, it's more healthier, but that has a toll on the cell which is slowly charged, because it is not charged, and that stabilized voltage will never be reached. So this could cause deterioration of a cell altogether. So that is the reason cell balancing is very important. So what cell balancing does is, the BMS, while doing a cell balancing, when it is put to charge, it will set a voltage level, say, or in the first image, where we see all the cells are at the same voltage window, which means all at the same level. Now, how is that achieved? Is, for example, we have cell 5, let us take cell 4. We have cell 4, it has reached its state 3.88 or near to 3.88, it is the first one to reach. Whereas the cell 7 is taking time. When it reaches 3.88, the cell 4 is not allowed to charge above this limit. So what happens is it stays over there, and the extra current or power coming to it either is dissipated as heat or it is transferred to the other cells, so that the other cells are charged quickly until cell 7 reaches its threshold normal operating temperature value, normal operating voltage value. So that's how it manages and says all the cell to remain at the same voltage level until there is 1 or 2 or 3 cells which it has reached its point, but it will not allow those cells to be charged more further, so that the voltage is still remaining constant over. So that is what the cell balancing does. It doesn't allow the cell which is charged first to overcharge. It will still be there, it will still receive the charge, but either it can dissipate the charge as heat or it can transfer its charge to the other cells, so that the other cells can be quickly charged. So this is how the cell balancing works, and it is the most important part of the BMS to function, the cell balance. So there are two types of cell balancing. One is active cell balancing and passive cell balancing.
So this cell balancing, as I have discussed in the previous slides, as I said, that when it is an active balancing, the cell which is charged first
will send its charge to the another cells which are not yet charged. By doing this, the time for charging is reduced, because so other cells need not wait for the charger to send the power. The power which is coming from the overcharged cells is also coming to that cell. In that way, a lot of time is saved. But there is a huge electronic circuitry involved in doing that, and this active balancing consumes a lot of energy, and it consumes almost 3 to 4 times of what the passive balancing BMS would do. So active balancing is actually more complex, but it is very effective and it is very costly solution. So that is what an active balancing would do. So that is what it happens. Like for example, if we have 10 cells and 10 cells, one of it is fully charged and other cells are not fully charged, without any balancing it would run into a thermal runaway state. But by doing this active balancing, the extra amount of energy which it is being received is being transferred. But whereas in passive balancing, what happens is we have the same nature over here. But in passive balancing, instead of transferring the charge to the other cells, it dissipates the whole charge as heat. So which means that is not utilized in any form, but it also doesn't allow the voltage to build up by charging. So that is one advantage of having a passive balancing. At the same time, the circuitry of this passive balancing is quite simple, and it is the most widely used balancing technique across, though it is very economical when compared to active balancing, and also the power consumption by active balancing is moderately less when compared to active balancing. So the next slide, now we will discuss on the voltage cutoff limits through BMS. What happens when we apply the voltage cutoff limits through BMS? So usually BMS is nothing but an electronic board which we need to program the voltage limits according to the user's needs. So this can be done as and when required. It is all dependent on us. So what are the voltage cutoff limits for the BMS? Let us just understand as per the chemistry again. What is this? For a typical LFP, lithium iron phosphate cell, we can see a maximum voltage is to be 3.6 volts, and the minimum voltage when it is discharged is 2.5 volts, and the nominal voltage is like 3.2 volts. And as per the manufacturers, we can expect a little bit of variation in this voltage level. And when it's an NMC cell, we have a maximum voltage of 4.2 volts and a minimum voltage of 3 volts and a nominal voltage of 3.65 volts. Hence, there are the chemistry standard, like these are chemistry standard voltage values which cannot much vary. Therefore, this voltage limits, as we understand, like these are the lower and higher voltage bands for a specific LFP and NMC chemistry, which have higher stresses at those ends of the voltage, and therefore when we chop off this end stress limits, we can reduce the stress and improve the cell life. So that is the reason where we always have to understand what are the voltage cutoff limits and chop off there. And by doing that, what do we get? By doing limits, what do we get? Now let us understand that with a pictorial representation. How do we get a capacity fade due to DOD limit? Now we have a cell which is having a voltage, we have assumed an NMC cell which is having a minimum voltage of 2.5, and it has a rated capacity of 3.25 Ah, and it has a maximum voltage of 4 volts. Now we have assumed a voltage cutoff of 2.8 volts. That means we have programmed the BMS to have a minimum voltage cutoff at 2.8 volts, and then which makes the usable capacity to 3.3 Ah only. So now let us understand the capacity fade due to DOD limits. Now this is a graph which we have assumed for an NMC cell which is of 3.25 Ah, and let us see how the capacity falls due to DOD limits. Now this is the actual window which is having from 2.5 volts to 4.2 volts. This is the maximum voltage and this is the minimum voltage. For that, when we have a standard condition which is 0.5 C discharge, we can see that it has a rated capacity of 3.25 Ah. Now when we chop off the charge stresses area and we make it the maximum voltage 4 volts and we limit the minimum voltage to 2.8 volts, we could see the portion where we have removed, there is a capacity drop, and that comes to usable of 3.0 Ah, which means when we chop off the voltages, we can see that there is a voltage drop. But by doing that, we limit or we eliminate the charge and discharge stresses, which helps in improving the life cycles of the cell. So what are the advantages? Now let us, as we saw the presentation, now we'll understand what are the advantages of the DOD limit. Now when we see what are the advantages, we can see that there is a capacity fade. Could not be an advantage, it's a limitation, but the usable capacity is less than that of rated capacity. But the cells will never witness any of those voltage threshold limits. So by doing that, we are avoiding high temperature generations, avoiding high internal resistance, and by doing this the life of the cell is increased, which means the internal heat generation is parallelly reduced. And also at the end of the maximum and the voltage band, where we have double or triple times of internal resistance rise up when we saw in the previous week, that is eliminated mainly. And one of the most important thing is SEI layer formation. So when the cells are not stressed so much, the SEI layer formation happens slowly. It is gradually, the speed of it is reduced, and by doing that we won't allow the cell to witness its thresholds, and the SEI layer is usually responsible for the dendrite growth or lithium plating on the anode, which causes internal short circuit. And the reason for that formation is something which we have attacked, and we have reduced that to a greater extent that the SEI layer would form, but it would not form at the rate at which it has formed by controlling the DOD limits. So that is the advantage we get majorly, which means the life cycle of the whole cell can be increased. Now we'll understand what are the BMS C rates and protection features. So we have till now understood what are the parameters like voltage cutoffs, cell balancing, and also a few terminologies, and which are the basic functions of BMS. Now we would also go through the BMS protection features. Here BMS charge protection feature. So here we can see a cell is being charged based on a common charge protocol, which is CC and CV, which means CC is called constant current and CV is called a constant voltage mode. Initially the battery pack is charged at a constant current always and up to a certain amount of voltage build, and then the charges enters into a constant voltage mode, and which means the voltage is constant and for a small duration of time, and then the that is basically for stabilizing the voltage, and also the cell reaches the maximum capacity required. So here is the graph which we can see there is a voltage and there is a capacity, and this is the current. So basically if we see when there is a constant current being passed, you can see voltage builds up slowly. It slowly gradually builds up. It has reached its point, and then after a certain time it will not increase anymore and it's into CV mode. It has become a constant voltage, and the current also slowly drops hereafter. But if you see the capacity curve, it still needs some more time. After the CC mode, it still needs some more time to build its 100% capacity, and that is where which happens in the constant charging mode, constant voltage mode. So there are two modes, constant charging and constant discharging, but still that happens. But if you see at the current, it still drops, but there is still certain amount of current which is still be going to the cell. When that is there, the BMS which usually does is it stops charging after the minimum current it has reached. For example, if it is charging at 0.5 C over here, if you see it is charging at 0.5 C, which is 1625 milliamperes, it will charge up to a constant current mode, and at a constant voltage mode you can see it is gradually reducing. So which means we have to program the BMS saying that if it is reaching a 0.2 amperes or 0.1 ampere, the charge will completely cut off. So the BMS will not allow any more charge to go to the cell because it has reached its threshold of 4.2 volts and it has also reached its capacity which is meant to be. So that is how you program the BMS as 2.5 volts, 4.2 volts as a maximum voltage with a cell capacity of 3.25 and C rate. If anything is going more than that, the BMS would definitely disconnect it and maintain that once it is reached its 4.2 volts and the required current rate is met, the BMS terminates it. So what happens if this is not working? So you might have observed in your daily life scenario when most of the people have a habit of putting your cells for charge and you leave it overnight. Initially for the first 1 month or 2 months or 3 months or 4 months, if it's a brand new cell, you would not even observe that. But what happens is your cell is, even though if it is cut off, your cell will still be receiving that amount of charge slowly. And when that is done over a period of time, your cell is deteriorating because it is constantly at a high voltage. When a cell is at a constantly high voltage, as we saw in the previous graph, when it's always at 100% SoC, your internal resistance is always high. And there is no way that your cell is being discharged because the charge is being pumped in, and when that happens, your life is going to be affected. So after a period of time, your cell, your mobile phone which you would be using for a whole day without any charge would slowly reduce to maybe instead of 24 hours a day, it would reduce to 23 hours and then slowly it will come down to 24 hours. And then one common tendency what we all feel is, now it's been few days, it's been few months, now the cell has started deteriorating, let us change to a new cell. But that's not the case. It's because of the human pattern that is happening. We are forcefully allowing the cell to deteriorate by allowing it to charge for a longer period of time. So that is what happens with BMS. So the same happens with the BMS charge protection. Even if BMS has to disconnect it completely. Even if it is disconnected, we should be careful enough that it is not anymore connected to the charger, because there will be certain amount of charge which will always be flowing through it, and the cell or the battery pack will always be at high voltage potential where the internal resistance is always high, and a cell or a pack having such high internal resistance is not good at all. So that is the BMS charge protection feature, where the BMS actually disconnects it after it reaches its maximum set voltage range. Then we have the same for discharge protection. So when we have discharge feature, the maximum voltage is 4.2 and we have a minimum voltage of 2.5 which is chemistry dependent. Once the voltage is reaching its 2.5 volt, it will disconnect at that point of time. So here I would like to emphasize something more, which is actually to make you understand what is the capacity and its C rate availability over here. Firstly, let us understand the BMS protection feature, which is like, now the cell has been discharged completely and it has reached this 2.5 volts, and after that the BMS would cut off, and anything, if the motor or the controller is asking for more power, the BMS would straightly communicate that there is no more power, and the BMS terminates the whole command itself there. But if we want to have higher discharge capabilities, if we want to discharge for a longer time, as we know, 0.5 C is for 2 hours, 1 C is for 1 hour. But it would also have an impact on the capacity delivered. Now, if we see, there are 3 graphs, 0.2 C, 0.5 C and 1 C. 0.2 C is something, when you discharge at 0.2 C, you can see that 0.2 C is actually more than what the typical capacity of the cell is. The cell is actually of 3.25, and this 0.25 C, if it is extended, it can go up to 3.3 or 3.4 Ah. Whereas if you see 1 C, it is limited to 3.25 only. So, which means if you
discharge the current at smaller or standard rate, the kind of power which you can discharge or deliver would be slightly higher than what your actual normal condition is.
So, which means you will also have to choose the right C rate as per the load profiles. When a battery pack has to be designed, when a battery pack is designed for an application, you should also see that what is its C rate, and when you choose a cell, you should also understand what the cell can deliver at that C rate and how is its capacity being affected. Here it's matter of 0.5 or 0.25 Ah, that is fine. But there are some certain cells which can have a major impact when you operate at 0.25C and 1C and 3C, which we saw in terms of internal resistance. That is the same which would happen for this as well. So it is very important to see that where do we limit our C rate, how much of it has a capacity difference when it is discharged at a lower C rate, and how is that capacity difference being affected when it is discharged at higher. So nevertheless, the BMS is being programmed with that protection feature of saying if it is reaching 2.5 volts, anyhow it's going to be disconnected, and also it's also going to have that protection feature that it is going to be discharged at higher C rate even though it is going to disconnect it. Then we have one of the most important feature, which is BMS temperature protection feature. So as we know, whenever the cells are operated above the operating temperature, there could be an impact. Like the main reason is like the electrolyte which is there in the cell could dry up, and that would leave no medium for the ions to transfer. So the BMS helps in monitoring those hotspots. Like we discussed, like we know that there are NTC sensors placed throughout the battery pack, and those hotspots are actually arrived by doing a thermal simulation and understanding where do we have a hot, and by placing the NTC sensors at that place, the BMS can take an appropriate action to stop or limit the C rate. Like for example, if the battery pack has reached its maximum temperature, that is not throughout the battery pack, it could be only at a hot spot where the sensor is. That means the other portions of the battery pack are still cold. By doing that, BMS has two ways. Either it can terminate the whole battery pack, or what it could do is, instead of discharging at 1C or 2C, it can slightly reduce that discharge rate. It can slightly discharge at lower C rates, maybe 0.5C or 0.2C. By doing that, it can still allow the pack to function, but at a lower C rate. So that is one advantage. That's how you can program the BMS to be more effective and more powerful. So this is one feature that you can always test it. Like for example, if you have your mobile phone, you could keep it under the hot sun, and you can feel that your mobile is warm. Then especially if you're using the latest 5G phones or latest phones, you can always have a display on your mobile saying that your mobile is hot and you have only limited access. So that is actually a protection done by the BMS considering the temperature that the cell has been experiencing. So that is one protection feature which you can do yourself, but I would suggest be careful when you are hitting your mobile while doing that. Then beside that, we have a graph which shows a capacity of a cell, and if you see, the capacity of that cell is being affected because of the temperature. This is a discharge curve, and we can see the charge is 0.0 to 45 degrees and minus 30 to minus 20 to 60 degrees. And here if we see graph or the line with minus 20 degrees ends up much more before the typical capacity, which is at 25 degrees is the typical rated capacity, which is something around 3.25 Ah. And if we see, if we are discharging the cell at minus 20 degrees, it is ending before 2.5 Ah. And what is the reason behind that? The reason behind that is simply this, that the electrolyte inside the cell is frozen and it doesn't allow a complete reaction to happen, which means the ions are not completely transferred, and because of that there is only little bit of capacity that it could offer at that period of time. So that is what happens when you are trying to discharge the cell at sub-frozen temperatures. So in that way you can see a drastic capacity fall because of that. So what you could do that is, you could put a heater onto the cells, allow it to heat it up to certain time, and then you can start using the cell. Also, this is certain thing that when you overheat the cell temperature, you have a separator between anode and cathode, which we discussed in the first week. That separator is made of polymers or PP material or something, and it's of nano size. And when such amount of heat is being transferred, when the cell is being operated at such high temperatures, the separator between the cathode and anode melts. And when that melts, the whole anode and cathode are in contact with each other, which causes internal short circuit, and it can also lead to flames. So that's the reason BMS has to be very cautious, has to be programmed cautiously for higher temperature and lower temperature protection, so that the cells are steady and they don't enter into a thermal runaway state. Now let us understand SEI layer and its effect on capacity degradation. So all the above layers like overcharging, discharging, overheating on the cells, etc., can lead to an SEI layer formation. And this is something which increases the resistance of the cells and further deteriorates the whole cell and kills the cell at the end. So SEI layer is nothing but a solid electrolyte interface, which is formed because of all the abuses like overcharging, we have over discharging, we have abusive higher C rates, we have high operating temperatures, and all these lead to a faster formation of solid electrolyte interface, and that is actually formed on the anode, which is the negative electrode. And let's get little bit into the basics of cell. Like we have a cathode, and which is a positive electrode, which is a composition of LFP or an MC, and we have an anode, which is basically of graphite and carbon. So during charging, what happens is all the lithium ions move from cathode to anode, and they sit onto the anode. And when we are overcharging it, all these lithium ions go and fix to the anode so badly that they are plated onto the anode. And when overcharging happens many number of times, this lithium ions, if we see, they are fixed to this anode portion. And when we are discharging, all these lithium ions move back to the cathode from where they have come from. So by doing this, the lithium ions can come sit on the anode, then they go back, and by overcharging it, some of the lithium ions still remain on the anode only. So when during the next process of charging, what happens is the next lithium ion which comes, it would not sit on the base, it would go and sit on top of the lithium ion. So what happens is by doing that, the lithium ion gets deposited one over the other and one over the other, like where instead of having a flat surface, we can see a lot of ions forming one top of the other, which could lead to dendrites. And when that dendrites are formed, the same happens when the dendrites are formed. It could puncture the separator sheet which is in between the cathode and the anode. That is where we get a short circuit, internal short circuit of the cell. And similarly, what happens when discharging? When we discharge the cell to a higher extent, then we are over discharging the cell. What happens is all the lithium ions which are going away are deposited on its cathode from where they have come from. And if we are over discharging the cell, the anode portion of it has a current collector which is made up of copper. And when we have such kind of copper ions, the copper ions also gets released, and because of which the metal contamination happens, and then again we have the same reason, which is the separator sheet tears off, and there is an internal short circuit between anode and cathode. So the reason why this whole thing happens is because of we are overcharging the cell or we are over discharging the cell. And we also have abusive C rates. So abusive C rates are like the same. When the cell is at lowest SoC like 5% and 10%, and even then we are trying to abuse the cell at 2C, 3C, when the BMS is not even bothered about that, that is where it happens, abusive C rate. And then what happens in the higher operating temperature? Nothing but the electrolyte gets dried up and there is no medium for the ions to transfer, and there could be salt remained on the separator sheet of the cathode, and that can cause internal short circuit as well. So there are n number of ways of SEI layer formation and the cell deterioration, and the main reason for that is the user's abusive usage, and if the BMS is not programmed properly, that is also one of the main reasons. So now we'll get into different types of BMS and classification. So the BMS are mainly classified depending on their functionality and working voltages, like high voltage and low voltage. Basically, we have low voltage and high voltage. In low voltage, class 1 is basically below 30 volts and 60 volts, and in high voltage we have two classes, class 2 and class 3, where class 2 is for less than 300 and 900 volts, and class 3 is for less than 1000, 1500 volts. Usually any voltage less than 330 to 60 volts are mostly used in two-wheelers and three-wheeler applications, and anything more than 300 are used for cars, buses, off-road vehicles, etc. That is how the whole BMS are designed for, and any BMS which is less than 60 volts are little bit simple in their operation, whereas high voltage BMS are quite complex in their operation because they'll have higher currents to handle, higher voltages to handle, and there are a lot of cells in the high voltage battery pack connected in series and parallel, and they'll have to balance it in a much more complicated way with much more accuracy. So that makes the high voltage BMS very complex, and it has a sophisticated architecture compared to a low voltage BMS which is less than 60 volts. The BMS classifications are basically into two types: centralized architecture and decentralized architecture. Now let us talk on this architectures for a little bit more time on centralized architecture. So when we say a centralized architecture, it is basically simple, and it is mostly used for low voltage battery pack applications, where the same BMS board houses all the electronic circuits. It has all the monitoring and controlling required for the pack on the same board. So the single board houses voltage sensors, temperature sensors, which is used for regulating, calculating SoC, SOH of the battery pack. It senses all the voltages of the cells. It monitors, and it also performs the cell balancing of the cell. At the same time, it also has temperature sensors where it can monitor the temperature of the modules and take the appropriate actions by the BMS itself. So this is what the centralized architecture is. Everything is done by a single board, and also it has a power distribution unit, which is like the power cables coming from the module are connected to the power distribution unit, and then from there it is going to the connector, positive side on the negative side connect. And then we have a BMS which can also have some optional features like or a smart connectivity app or a GPS tracking, etc. So the image shown here is a BMS board which can have a CAN communication, which can have a charger based communication, and it can talk to all the cells in the battery pack internally. It can talk to the external parties also, like the VCU or anything, through CAN based communication. So that is the BMS centralized architecture. Now we have the BMS decentralized architecture, which is basically for the high voltage applications. So what does decentralized architecture BMS mean? Like, it is mostly applicable where the BMS is split into two types. Like, we have BMS usually where everything is done on a single board, that is centralized. Whereas when we have decentralized, it works on the concept of BMU and BCU, or can also be called as master BMS or slave BMS. When it comes to BMU and BCU, BMU is called as battery monitoring unit and BCU is called battery control unit. So when it comes to a functionality of BMU and BCU, BMU monitors the voltages and temperatures of the module levels. Each BMU has certain number of channels, and as per the channels the BMU has, it is connected to all the cells and it monitors all those cells, and that information is sent to the BCU, and BCU there takes the control of what it has to be done, how it has to be balanced, and etc. So BCU is the controlling authority over here, but BCU directly doesn't get in touch with the sensors or the voltage sensors of the cells. It gets in contact to the BMU, where BMU monitors it and sends the information to the BCU. So the BCU is something which can also house the PDU, which is the power distribution board. Some of them allow, some designs allow for that, some designs do not allow for that, but the PDU is something through which the power lines of the battery modules and the cells are passing through the PDU, and it is controlled by the BMS. Usually all BMUs and BCUs are connected through a proper communication wire, so that there is no lag between the communication between the BMU and BCU. So usually in some cases this BMUs are also called as slave BMS. When it calls as slave BMS, the modules where the voltages sensors and the temperature sensors are connected, it not just monitors. When it calls a BMS, slave BMS, it actually performs a cell monitoring. It also takes care of the cell cutoff voltages. It also does the cell balancing, and it also takes all the does all the functionality that a master BMS has to be done, but it does only at a module level, and all this information again translated to the master BMS. So that's how the decentralized architecture works. So here is the image where we can see this is the master BMS, and here we have a lot of slave BMS, and slave BMS is connected to its own battery packs or battery modules. So this is a very big battery pack where there are different packs and modules, and each modules are connected to the BMUs, and all these BMUs or slave BMS are connected to the master. So this is how the decentralized architecture is done. So now, what is the need in HV for a decentralized architecture? So that could be a question. Why do we need that? So now if we see HV pack, let us take the case study which we did during the first week. We saw that there are 400 cells in a single pack with 20 modules each. Whereas for a low voltage battery pack, typically it's a 48 volts, and we can just have 16 cells with 2 modules with 8 cells each. So that is the case with a 48 volt. It's just 16 cells, and whereas for the high voltage pack we have 400 cells. Each module is of 20. Each we have 20 modules, and each module again has 20 cells in that. So remember, when we have so many cells and the area of the pack is so big, like 1.5 cross 1.5 cross 0.4 meters, just imagine if we want to connect a voltage sensor from this end of the module where the BMS and the BMU is on the other end of the battery pack. The wires it has to be run is across the perimeter, which makes it almost like 2 meters long. So that is the wire of a sensor that is needed. And it's not the wire of the sensor that is important over here. Most important thing is the precision of the measurement. So if we have such longer wires, these sensors would be prone to a lot of disturbances like noise, frequencies, etc. And there are a lot of electronic components where the signal or the transmission of the data might be affected. That is where the EMC comes into picture. So that is one of the reason where we would lose the voltage sensor's effectiveness because of its length of the wire. And also there could also be a lot of connection reliability problems that would come into picture, like the pack is subjected to a lot of vibration. And when such things happen, there could also be a situation where the voltage sensor can cut off or the connector might become loose, which means there is no proper reliability for the connections in such cases. So the sensor's wire, it is good if it is short because there is a BMU which is right next to the module and it gets connected to that, and there is only one wire coming from the BMU going to the BCU or the master BMS, which is okay. Instead of having hundreds of wires, just having one wire is fine, and it also ensures good reliability against vibration and shocks. And then versatility. Now when we say about versatility, each BMS can handle, for example, in a centralized BMS, it can handle only fixed number of cells, like 20, 30 or not more than that. When it comes to decentralized, you can always choose a master BMS which can handle 5 to 10 BMUs, and each BMU can handle 50 to 60 number of cells. Usually that is the product which is available in the market. So if you have 400 cells where each BMU could handle 50 cells, so you can have total 8 BMUs, and you can have a BCU which is having 10 channels for the BMUs to handle. So which essentially makes the whole architecture scalable over a period of time. You can reduce the number of BMUs, you can increase the number of BMUs whenever the modules are reduced or increased. So in this way, you can have different variants created when you want to design a battery pack for some other application. So this is something where you can have versatility in designing the BMS. So here is a sample wiring harness overview, and like we have a module with 14 cells and there are connected with bus bar, and we can see we have voltage sensors at every bus bar located, and we also have temperature sensors wherever we have hot spots, and all these are going to the BMS. Either it can go to the BMU or it can go to the BMS board. So now we'll understand what is the wiring harness. Like we saw in the previous slide, the wiring harness for the above slide where we saw 14 cells in a module. Each bus bar for series connection can be fixed with a voltage sensor, and that voltage sensor will help the BMS in stopping the cells for terminating when overcurrent happens or over discharge happens or higher temperatures are reached or abusive high C rates conditions. So these are the sensors responsible for monitoring the voltage of those cells, which goes to the BMS and where the BMS takes the appropriate action. So whereas in HV, this can depend on number of modules, each number of modules into the number of cells it has, and that also depends on the BMU's capability to handle that many number of cells. And if it is not able to handle number of cells, depending on the kind of number of cells, we can always add another BMU, and such number of BMUs can be added all together and which are finally connected to the BCU. So that is how we have a wiring harness overview for both. So low voltage or low voltage BMS or BMS for voltages less than 60 volt is very simple. Everything happens on single board, whereas the BMS for high voltage is quite complex, and that's the reason you need to split it into BMS, master BMS, etc. So this is the architecture for what we have. Here, for ease of understanding, I have taken one module and each BMU for that, whereas 2 or 3 modules can be handled by a single BMU as well. If we have a BMU with 60 channels or 50 channels also, which is readily available across. So here we can see we have a module, we have each BMU. All these BMUs are connected to the BCU, which is a battery control unit. And the positive line is in contact with the precharge contactor and precharge resistor. This is nothing but a precharge circuit. And this precharge circuit is responsible to save the electronics of the battery of the vehicle, controller and motor from high inrush current which comes from these modules. And apart from these modules, we have power connectors, we have OBC, which is nothing but onboard charger, and we have a low voltage connector, which is nothing but communication port, which is needed for CAN communication from the battery pack to the VC. This high voltage pack, like the low voltage, also consists of all the voltage sensors, temperature sensors, power connectors, etc. So those are all the critical parts of a high voltage battery pack. So here we have a HVIL loop, which is also a critical part of the architecture, which we would learn and understand about each and every part's role in the later slides. So this is how a HV pack architecture looks. It is quite complicated. Here it's quite simple in line diagram, but it becomes very complicated. So as we saw in the components HV architecture, so this is what it has. Like, there are a number of modules as per the voltage and current requirement. We have BMUs and BCUs equal to that of the battery modules and the number of cells in that. We have precharge circuit, consists of resistor, contactor and other wiring harness required. We have current sensors, contactors, and on the positive line, current sensor is something which is talking to the BMS to understand whether the right amount of current is being delivered or not, or if any extra current is being asked for. And then we have a master BMS which monitors the whole pack, and then we have wiring harness which includes voltage sensors, temperature sensors, low voltage connectors, etc. And we have H, as I showed, this is a loop, high voltage interlock loop. So that is something which is very important for the high voltage battery pack. So we discuss each of this component in detail once we have a case study done. So this is a case study for a high voltage pack. Now we have 630 volts, 200 Ah pack, consists of 3.2 volts and 100 Ah prismatic cell. Now for a series combination, we have 200 cells in series, and for parallel combination we have 2 cells in parallel altogether, which gives we get 640 volts. We have 200 Ah of capacity formed, which means the resultant pack capacity is 128 Ah, and we have module configurations of 20 numbers in 10s2. This is nothing but the case study we had. For this, what are the wiring harness details we have? Wiring harness would be BMUs or the slave BMS required are, since we have 20 modules, I am assuming that this BMS has only 20 channels, so we need 20 numbers. If the BMU is capable of handling 40 channels, then this reduces to 10 number of BMUs. If the BMU is capable of handling 60 channels, then this becomes to even more lesser. Like that, the whole BMUs can be sorted out how many BMUs are required for the whole pack. And then we have voltage sensors. So we have 10 cells in series for a module. So we'll have 10 voltage sensors throughout the module. And then we have temperature sensors. So temperatures are something which we decide depending upon the hotspots of the module through thermal analysis. So that is something which is open, which can vary depending on from one OEM to another OEM or from one result to another result. So now we start about the functionalities of BMS and other components used. So let us start to understand each and every functionality of the BMS and other components. So firstly, as we know by now that master HV architecture consists of a master BMS, and some of its major functions are like controlling the BMU boards, parameters received, and it has to also assess and evaluate all the controls. So BMS major functionalities, apart from controlling the C rates, controlling the BMU board parameters received, etc., it also have some optional features or some important features that are like it is responsible for controlling the contactors, the on and off position of the contactors. It is responsible for controlling the walls of the cooling plates, like the the kind of flow rates needed for a cooling plate to switch on and switch off, those are something which is controlled by the BMS, master BMS only. And it is also one of the monitoring element to understand at what flow rate the cooling fluid is being passed through. So it can also control that flow rate by opening the valve fully or opening the valve half, and that way that becomes the whole architecture more complicated, but that is something which can be integrated in the BMS to do that kind of controls as well. So basically the master BMS is basically responsible for communication with the VCU and the battery packs also. Another most important part is the precharge circuit. Usually the precharge circuit, as we saw, it consists of a resistor and a precharge contactor, and it is basically used to withstand a high inrush current which is coming from the battery pack when the ignition is turned on. When the circuit is open, what happens is there is a high inrush current because the battery pack is fully charged and it's a very higher potential. There's a tendency that the voltage always moves from high potential to lower potential, and when the ignition is turned on, that means when the loop is turned on, the other components in the EV driveline like the controller and the motor have much lower voltage potentials. So when such high inrush current comes in, there has to be something to stop such high inrush current so that the electronics and all the wiring harness etc. are not damaged because of such high inrush current voltage. And that is the reason why we have a precharge circuit where the resistor and the contactor there stops most of the inrush current, and this is for a very small fraction of second, maybe 0.5 seconds or 1 second, and then after it becomes normal. So this is equal to that of I would like to draw an example over here. Like for example, you have a water tank which is fully loaded with water, and when you switch on the tap, the water gushes out with a full force, and later on it becomes very normal. So this is also the same, but when such high pressure is coming up, you need something to hold. So that is what the precharge circuit does over here. So this is what the precharge circuit function is, and that is actually the contactors are all operated by the BMS itself. And then we have HVIL, which is called as high voltage interlock device or interlock loop, which is necessary to provide the contactor interlock to detect wherever there is a poor connection between a HV or there is any open circuit where that could lead to a live connection and it can cause electrocution. So it is very important to understand where there are any open loops and all. If there are any such open loops, it would send a pop saying that there are certain loops which are open. So that is something, a protective feature which is a part of BMS to handle it. Now this is how a high voltage architecture functions.
It doesn't mean that the Indian lives are not as expensive as the others' life, not like that. It depends on many political factors also, the cost of the vehicle, the cost of living in India, per capita income of Indians, everything is being considered before these norms are being deployed. So only if the vehicle with the norms available should be tested for during the design and validation, no. Even an automobile passenger car is developed for India, the same set of tests which we do for the other markets, the USA market or Euro market, that also should be done for the vehicle which is planned to be launched in India. Even though there is no regulation proposed by the government, still the automobile manufacturers test it because to have safety of customers in mind. So safety, it has to be addressed in many ways. Safety issues comes from the frontal crash or from the side impact or from a rollover, or it can be from fire also. So there are many areas which should be touched upon by safety and should be addressed during the design and development phase. And the third element is the endurance. Of course, any product you buy should have some life. You buy only if the product is durable. You buy a slipper, you will think that that slipper will last for at least one year. If it is not lasting for 1 year, you say the quality is not good. So this is how the endurance is being judged subjectively by the customers. But from the automotive manufacturer's point of view, this endurance has to be measured. So how to measure? is basically what type of road the vehicle is going to be driven and how many times the vehicle is going to get some abusive loads like this, people traveling over the vehicle, and how many times the vehicle is going to ride in the terrain road, in the muddy road or in the hill station roads, and how the luggages are being going to be mounted in it, and how the dynamics of the vehicle is going to handle the road situation of a particular market. So everything should be considered, and it should be measured, and it should be defined. So that is how the warranty systems basically come. So if a manufacturer gives the product warranty as 2 years or 4 years, he must have designed it for that endurance limit. So endurance is the third element which the design and validation mainly focuses. And the fourth is the comfort and performance. Of course, this is a luxurious item most of the time, so not a basic requirement, but still the market is now emerging. So the audience, the customer's expectation is now changing slowly from the mindset of basic need to the comfortable need. So you should think about the fuel economy, the power of the engine. You should think about the aerodynamic drag. You should think about the NVH, how the noise is being perceived inside the vehicle. You should think about the ergonomics. So there are many other factors which are involved. So this is one element which should be considered during the design and validation phase. So once you do the design and validation, these four elements will basically cover your need of the design and validation phase. Just to give you an example of the previous V model the details of the previous V model explanation. At first, we designed the automotive. So this comes from the requirements step in the design phase. So you decide how the automobile looks like, what are all the different systems involved. This will be a basic image. And then you design the systems. First, you design the automotive, you conceptualize the automotive, then you conceptualize the system and design it. So you divide the whole car into different systems. You divide it into a structural member called the BAW, powertrain as a different system, brake as different system, steering, your harness. You divide, and many more systems are involved. So you divide the whole car into a different system. And then each system will be divided into different components. So here you see, I have taken the example of a BAW. So BAW cannot be just like that designed. So each and every part detailed design should be required. So this is what we call as the component design. So how the cross section of each pillar and each structural member of BAW should look like. What are all the controlling parameters? For example, these parts are basically designed using the force displacement requirement. And how the door hinge is being designed and how the hub of the tire is being designed. So like this, each and every part of the system itself should be designed in detail. And then it comes for the validation step. So once the design is made, it comes for the validation. This validation can be done either virtually by using CAE, the FEA, is a finite element analysis methods, or by the physical validation. Of course, physical validations are much costlier compared to the digital validation. So digital validations are usually done in the beginning stages of the design and development stage, and the final validation will be obviously done by the physical step.